everybody, and welcome to Azure Cosmos DB Conf 2025. My name is Patty.
And I'm Marco. Welcome to Azure Cosmos DB Conf, which is co-hosted by Microsoft and Azure Cosmos DB community. You're going to hear some very exciting things about the latest innovations in Azure Cosmos DB, the database for the era of AI.
That's right. This event will include everything from product team members, customer stories, and real-world use cases. As a matter of fact, we had over 100 submissions that we pared down to what you'll see today.
We are going to have some exciting sessions coming up. For example, vector search powered by DiskANN, RAG applications, agent apps. You're going to hear about serverless and also cost savings.
Well, it sounds like we have a big show ahead. But before we start, I do want to mention our code of conduct. We want to create an inclusive and welcoming space, and we hope that the content that we have reflects that. With that, please use the Azure Cosmos DB YouTube stream chat to interact, share thoughts, ask questions, and as a starter, please let us know where you're watching us from. Then, please use hashtag Azure Cosmos DB Conf on social, where you could be featured. Lastly, check out the resources on our website, including our Azure Cosmos DB Challenge, our evaluation form, and ways that you can get started using Azure Cosmos DB. And as a quick reminder, all sessions will be available on demand.
Yes, all the sessions will be available on demand. And so, without further ado, we are going to get started with the keynote delivered by the Vice President of Azure Cosmos DB Engineering, Kirill Gavrylyuk. But before we go there, let's take a look at a short video and see what our customers are doing with Azure Cosmos DB.
From work time to fun time, Azure Cosmos DB powers the apps that power your day. Rise and shine with personalized mobile and online experiences powered by Azure Cosmos DB. You get your Starbucks coffee your way. Gas up and go. Real-time vehicle diagnostics let you know if your connected car is low on fuel. Going up, no time to take the stairs. Predictive maintenance means a smooth and safe ride to the 10th floor. Sign in, say hi. The consistent reliability of Microsoft Teams keeps the collaboration going wherever you are, using Azure Cosmos DB as the primary data store. Learn something new. Built on Azure Cosmos DB, ChatGPT's always ready to answer your questions and converse with context. See who called. Secure storage means your AT&T voicemails are ready when you are. Order up. What were the groceries you ordered last week? Walmart makes reorders easy with all transactions served by Azure Cosmos DB. Check your balance. Fidelity's secure real-time transaction processing means real-time financial management. Finally, vacation. No sitting on the tarmac for you. Azure Cosmos DB powers fuel management for JetBlue. Your modern life is built on modern apps, and modern intelligent apps are built on Azure Cosmos DB.
Hello, and welcome to our 5th annual Azure Cosmos DB conference, the conference for community by community. Cosmos DB is used in every day of our lives. It powers many of the apps we use daily. It powers all of Microsoft Cloud apps, powers the world's fastest growing consumer app, ChatGPT. And there is a good reason for it. Cosmos DB is AI ready. It offers built-in vector and hybrid search over schemaless semi-structured data. It runs world's mission-critical apps thanks to its active-active multi-region write ability with 5 nines availability and millisecond latency guarantees. That's right, always available with 4 replicas always, and multi-region writes give you availability no matter what happens. Even if the entire region goes down, your Cosmos DB will be available. It is serverless with 2 convenient serverless pricing models. You can pay for transactions, or if you have high transaction rate, you can pay for transaction rate for throughput with instant automatic scaling without limits. It comes with developer-friendly schemaless data model and APIs, including world's most popular API, MongoDB API. And might I say, it is the cheapest, fastest, and the best MongoDB API among the cloud services for MongoDB. It integrates really well with Microsoft Stack, AI Stack, App Stack, and Data Stack, Microsoft Fabric. Just to highlight a couple additions since our last Cosmos DB conference, we rolled out dynamic autoscale, saving customers up to 80% cost. We rolled out built-in vector search and full text search. No longer you have to duplicate your data and move data to another search service, and many other capabilities. Take, for example, change feed. I would like to invite Andrew Liu, our fearless group product manager, to join me and demo the recent addition to Cosmos DB change feed, preserving all versions and deletes. Andrew, please take it away.
Hey, Kirill. I've got some exciting updates to share both with you and our audience here on Cosmos DB's change feed. I should probably first level set. What is Cosmos DB change feed and why is it interesting? The simplest way to think about change feed is akin to exposing message queue semantics from within a database. Elaborating a bit here, change feed provides a persisted, ordered stream of changes from within your Cosmos DB containers and exposes them in the order they occur. It enables you to build reactive applications that respond asynchronously and incrementally to data changes. You can read the change feed multiple ways, whether it's through the SDK via two modes, a pull model or a push model, or through integrations like triggering serverless Azure functions. Reading is scalable and leverages Cosmos DB's distributed backend. It reads in parallel from each of the Cosmos DB underlying partitions. By leveraging change feed, developers can efficiently create scalable and resilient applications that are tightly coupled to the continuous flow of their data. Now, a frequently asked question I get is, what can you build with change feed? Common scenarios I've seen include are event-driven architectures or event sourcing. I'll explain this one a bit. An example of event sourcing is order processing pipelines in large-scale e-commerce systems. Orchestrating many microservices such as checkout, payment, order notification, fulfillment can be challenging. And microservices need to communicate to n-1 other microservices. That's an n-squared scaling problem. Now you can greatly simplify this by eventing the orders on a shared message bus. You also want to persist these orders in an index database in order to power experiences like showing the order status page to both your customers and your support teams. So why not just use a message queue and a database separately? Well, it's about resiliency. When I have a database and a message queue and use them together, when everything is behaving as expected, life is good. However, what about error conditions? If the app successfully writes to the database, but not the message queue, or vice versa. In those situations, you might show an order was confirmed, but it fails to make progress on payment and fulfillment, and your customer is left waiting. Alternatively, you might process it for payment and send it to fulfillment. However, it's left in a pending state, lending to a lot of confusion. And as you go and look at all of the different permutations of orchestrating n to n-1 microservices, this can require a lot of complexity in the error handling. Building an event store over change feed enables you to reconcile the truth between the database and the event bus. Other examples here, of course, include data auditing, real-time analytics, such as stream processing and data movement. And when you do that data movement, you can go and add additional processing, such as aggregating over a stream processor to build leaderboards, or implement design patterns, such as global secondary indices. Now, what's new here is the new change feed mode, all versions and deletes. With all versions and deletes, this is different from the existing mode where we would surface every insert and update and avoid the write amplification. In the original change feed mode, it would only keep the latest version of the record. Now, the advantage of that is if I update, let's say, a 1 kilobyte record 10 times, it only occupies 1 kilobyte in the database. However, there are other use cases where you want the complete history, where you want to have all of the incremental versions as well as deletes. This gets stored efficiently in the underlying log that powers Cosmos DB's point-in-time recovery for backup restore. And where this becomes very useful is if you have use cases like detailed audit logs for compliance, or you want to add resiliency to data processing pipelines where you need to be able to reliably reconstruct past states of data. So let's jump into a demo real quick. I have a canonical scenario here where I've built a game on top of the Cosmos DB change feed. It's a fairly simple game where it's a dice rolling game where I can go roll the dice and based off of that get achievements. Now, where change feed commonly gets used in gaming, of course, is to power both multiplayer and social gaming so that you can broadcast gaming events to other players, as well as to build aggregates where you stream process a leaderboard. And you want to make sure that you're not doing heavy aggregation queries. In order to get short millisecond, fast responsive apps, what you want to do is you want to pre-materialize into a view. Now, as I look at this game, let's take a look at how do I attach this to the change feed. First, I'm going to go to my Cosmos DB account, And enabling the change feed is very easy. I go over to features, and as you can see here, there's an all versions and deletes change feed mode. I go and turn that on. Now I go into my app, and what I'm going to do here is I'll restart the app. I'm going to go read the change feed. And reading the change feed is actually very straightforward. I can go and use, this is also new, we've expanded the SDK support of change feed, including the Python SDK. So I'm using the Python SDK here to query the change feed. And as you can see here, I'm also going and taking a look at injecting the mode all versions and deletes. As I get the responses for that, that gives me both the document body as well as some metadata. I can go and track to see if it's a delete, a replace, and base that, build conditional logic off of the body of the document. And so if I go and put this side by side with my app, as I go and roll the dice here, as you can see in real time, I am able to go and track the events directly from the change feed. We're going to do a deeper dive in change feed later at Cosmos Conf. We're going to have a wonderful session with Justine. But with that, back to you, Kirill.
Thank you, Andrew. This full fidelity in change feed simplifies many use cases. If you have a situation where you have many copies of the data and you're doing double writes, take a look at this. Now, Cosmos DB offers flexible, schemaless data model and APIs, including popular MongoDB API. Cosmos DB vCore for MongoDB is a relatively new offering, but rapidly gaining popularity as a faster, cheaper, and better MongoDB. It is consistently 20% cheaper than MongoDB Atlas for any SKU, with simple, intuitive vCore-based pricing. It is faster and better than native MongoDB in many use cases, not every. And it is open source under MIT license. That is right, you can fork it, run it on premises or your favorite environment. No strings attached. Permissive MIT license. Dynamic autoscale was probably the most popular addition of 2024 to Cosmos DB. It is now adopted by more than 80% of Cosmos DB usage, responding instantly to workloads needs per partition per region. If only one partition is active, only one partition is scaled up, and you build only for one partition, the rest stays at minimum. OpenAI is a great example of Cosmos DB elasticity and dynamic autoscale in action. OpenAI grew from 0 to 400 million weekly active users, making it the fastest growing consumer app ever. And more than 200 daily database transactions. Cosmos DB is the main database used by more than 50 various workloads at OpenAI, including ChatGPT itself. What attracted OpenAI to Cosmos DB is seamless scalability. It just elastically scales as workload size multiplies, no need to worry about servers, and schemaless data model, allowing developers to rapidly change the app, not worrying about database schema. This schemaless capability is very important today, more than ever. Developers will build apps with the help of AI more and more. Because AI makes refactoring much easier, developers will do more refactorings. But refactoring that changes the data model is brittle. If you have to change the database schema, that means you're changing it in the schema, in the ORM, and in the application if you're using a relational traditional database. With Cosmos DB, there is no schema, there is no problem, and you do not need to do data migrations between different data models. Cosmos DB now has built-in vector search and full text search and hybrid search, where vector search results are re-ranked with full text RRF. Now, what that allows you to do is to not duplicate data between Cosmos DB and yet another search service. It is serverless and has the lowest cost per query and the lowest latency across all leading vector databases on the market. Not surprisingly, CIOs named Cosmos DB #1 choice for AI database in a recent CIO survey by Bloomberg. Cosmos DB is used by many AI use cases today. Here are the most popular ones, and you can find samples on GitHub for each of these use cases. Next, I am honored to be joined by Kunal Mukherjee, Vice President at DocuSign, who will share with us how DocuSign is solving the $2 trillion agreements problem with the help of Azure Cosmos DB, both availability, elasticity, and AI, and schemaless. Let us invite Kunal on stage. Hi Kunal, great to have you on our show. Could you tell us briefly about the $2 trillion agreements problem?
Thanks, Kirill. Great to be here. Let me start with an obvious fact. Every single one of us signs documents digitally, many of them with DocuSign. And now for some numbers. We have around 1.6 million customers who send out documents for signing and a staggering 1 billion. Yep, you heard me right. Billion with a B signers. That makes for a staggering number of documents. The sheer scale of that makes it infeasible until now to figure out how many documents are coming up for renewal, by which date, and what would be the consequences of not acting in a timely fashion. To provide a concrete example, I have found myself locked into a lease on both a house and a car in my past life because I lost track of renewal dates and terms, as I suspect have many in this audience. Now consider that some large enterprises and even governments have standardized on DocuSign for digital signatures of every single of their agreements. The sum total of all of that scale adds up to a staggering 2 trillion number.
That's incredible. Agreements are so fundamental to our lives. This is our relationship graph, especially for corporate. Precision of search recommendations over that graph must be crucial. Where do you guys store all this data, and how do you search it and vectorize it?
Great question. We use Cosmos and SQL. SQL to catch all of the e-signature transactions as they happen, for which we, of course, need asset guarantees, similar to an ATM. And Cosmos, which stores what we call the brains of our agreements by way of the agreement data model that we call ADM, where we store industry and vertical standard schema and metadata, including AI-inferred metadata about individual agreements, so as to make them actionable and essentially solve that $2 trillion problem you alluded to earlier. We need to vectorize in order to provide search precision, take into account domain, jargon, etc. And we are moving away from search systems to Cosmos, which provides built-in vector and search capabilities, all in the same place.
This is very interesting. We observe this trend generally for databases and for Cosmos DB specifically. More and more customers move to use Cosmos DB for retrieval and search. How did you arrive at that conclusion?
It's pretty simple when you boil it down. DocuSign is a SaaS offering, and we need to provide performance and availability and to ensure seamless experience. Documents, summaries, metadata, etc. are all already stored in Cosmos DB. We needed a retrieval system that used the latest state-of-art algorithms, was cost-effective, and multi-tenant. Cosmos with DiskANN implementation is 60 times cheaper than in-memory counterparts that we evaluated and provides reliability and security guarantees that we need. Semantic retrieval and natural language interactions is simply the next step in the evolution of database queries.
Thank you so much, Kunal. Super grateful for having you as a customer. Given schemaless and horizontal scale nature of Cosmos DB, it is purpose-built for AI scenarios, especially for multi-tenant SaaS offerings like DocuSign. Most of Microsoft Cloud uses this for precisely these reasons, and so do many SaaS products.
Thank you.
This was enlightening. Schema flexibility of Cosmos DB, in addition to built-in semantic search, really opens up new opportunities for the apps, where you don't have to move your data and you get serverless retrieval system on semi-structured data. Now, today happens to be tax day in the United States. Stressful day for many of you. Let us hear from Vin Kamat, principal architect at H&R Block, on how reliability and elasticity of Cosmos DB, as well as its AI capabilities, help H&R Block navigate the peak of peaks of tax season with ease. Let us invite Vin on stage. Hi, Vin, and thank you so much for joining our Azure Cosmos DB Conf keynote. Could you describe how H&R Block has utilized Azure Cosmos DB to support both AI-enabled and non-AI applications, and what benefits have you observed from Cosmos DB in your applications?
Sure. We started our journey of cloud modernization several years ago, and we needed an ecosystem of services in Azure that all work together and on the Azure stack. So one of the obvious ways to do that is to use cloud native services. And in our stack, we started using Azure Cosmos DB. And one of the reasons is because it offers schemaless data model with domain-specific boundary-driven data, enabling distributed replication and scaling features. Those were really important for most of our mission-critical Tier 1 tax systems, which we call modernized tax systems. Now, there are other AI-enabled applications that we started to work on in the past few recent years, like 2 to 3 years. We started to, also use Cosmos DB for storing various types of other data that's specific to AI applications, such as chat history, user state, prompt variants, user feedback, etc. So the benefits, if I have to speak about the benefits, they are primarily around enhanced flexibility, scalability, operational efficiency, cloud adoption, which is going to be accelerated as you move through your rapid application development. All of that, enabled us to move faster to the cloud and then sustain that and mature in that space. One of the other things that I would like to highlight is it really enabled our event-driven architecture, microservices, and the fantastic JSON document support provides the ability to store high volumes of data attributes, which is really important for a fintech company like ours.
That's really awesome. Could you share specific examples of how Cosmos DB enhanced your AI apps, such as the AI Text Assist feature, and the improvements in client satisfaction and conversion rates?
Absolutely. We launched AI Tax Assist almost, a couple of seasons ago. And since then, we have seen a rapid adoption of it and incremental uplift in conversion of clients that use AI Tax Assist compared to those that did not, with also increase in conversion rates for new clients. So AI Tax Assist, the persistence layer or the backbone for it is Azure Cosmos DB. So we use all kinds of other Azure AI services in the architecture of the system, but Cosmos DB forms a key enabler in providing storage and data. So, like I said, chat history, user prompt variants, user feedback, benchmark testing data, all of that is supported by the storage that we have in Cosmos DB. The Azure and .NET ecosystem make it seamless to dive in, experiment, and deploy apps. And with our partnership with Microsoft, we have close collaboration and especially product support that also accelerates our solution to market becomes really possible.
It's very delightful to see the success when you success with a particular investment using our platform. How has the transition from SQL Server to Cosmos DB impacted the performance and scalability of your app, particularly during the peak tax season?
Sure. We still have many tax systems that still use SQL Server for RDBMS data to support critical operations. But we have several modern tax platform systems that use Cosmos DB. And because of its high scalability, navigating peaks of the tax season is not that difficult anymore. We're supporting high transactions volumes, achieving 400 to 1 million RUs, depending on the scalability. And also that enables us to prepare millions of tax returns during a very short period of time. And it becomes really important for us to ensure that the flexibility and operational efficiency, along with the scalability, make sure that the peak season goes without a hitch. So there are some things that we pay attention to for dynamic scaling and partitioning. But other than that, once you have matured enough to do that, then it all becomes part of the operations.
That's great. And today is a tax day in the United States. So this is your peak of peak, right? How is Cosmos DB working out for you?
No, it's been fantastic. We've had a great tax season. We look forward to finishing it really, really strong. And as I already mentioned, lots of things have come together, focusing on quality and resiliency. So over the past several years, we have made sure that we serve our clients, tax pros and associates, who all work. All of the associates always work and make sure that we serve our clients and tax pros first. And in order to do that, we need to have a very robust system in the cloud that can serve them during these peaks of the tax season, especially April 15th. And a couple of things I would like to mention is that when you look at some of the capabilities, especially Cosmos DB offers, along with a whole bunch of Azure services, one of the things that it has helped us do is streamline data gathering processes. And that really helps our tax pros and our engineering teams save time. And overall, I'm really excited about looking ahead, all the capabilities that are recently part of the Cosmos DB feature list, especially vector search, the DiskANN support, the auto indexing data, data analytics backing store, leading up to Fabric is another thing that we are looking forward to, and real-time BI layer. So those are 4 different capabilities that we are looking to experiment and in future, hopefully, adopt them. Thank you.
We're excited too. Thank you so much for joining our show and being our customer.
Thank you.
Well, this was a really great example how Cosmos DB elasticity helps customers scale for the peak dynamically, no over-provisioning of resources required, and how built-in AI capabilities help H&R Block improve engagement with customers. Really great story. We have only briefly touched the surface area of use cases trending today with Cosmos DB. I hope you will enjoy the conference and learn something new today. With that, let me invite Patty and Marco back on stage. Over to you, Marco.
Thank you, Kirill. This was amazing. By the way, I'm looking at the chat here, and we have some fans there. We want to say hi to Hon Lee, who is from London. We have Kevin from Kenya. Then we have Juan from South Africa and Atir from New York City. So hi there. I'm glad that you guys are enjoying the show. And so, Kirill, this was amazing. It was really interesting for me to really see how DocuSign is storing all the documents and the metadata and summaries, as well as the vector data in Azure Cosmos DB, and then use vector search to retrieve the information really quickly from there. And I'm always very excited about real-time, anything real-time really. So it was really fantastic to see Andrew's demo and see the improvements in change feeds. Patty, what is your feedback about the Kirill's keynote?
Yeah, well, I mean, first of all, Andrew's demo was so amazing. Andrew always has great demos.
Absolutely.
I really love the H&R Block segments, and I loved learning how dynamic scaling can help everybody do their taxes with reliability and ease while saving their costs.
That's amazing. By the way, Patty, have you done your taxes yet?
No comment. But anyways, let us know what you think. Please keep chatting, keep contributing, keep posting.
Yeah, we really want to hear your feedback, and please leave comments there. And also, by the way, by the end of this day, this conference, so we are also going to have a closing keynote delivered by H&R Block. So stay tuned.
Yep, you're right. We have a lot of great talks coming up. But first, let's hear from Andrew Evans from CarMax.
Hi, my name is Andrew Evans, and I'm a principal engineer at CarMax. I am tech lead on a team that owns an appraisal application used nationwide. Associates at CarMax use our application to appraise vehicles that we can buy from customers. My 2 main responsibilities are production support and managing our team. My day-to-day role consists of mentoring and supporting my team members, as well as making technical decisions for our application. We are using Cosmos DB to track appraisal data in our application. Appraisals are how we value vehicles that we intake. The appraisals that our application provides control how we purchase cars from customers for our business. We use collections in Cosmos DB to store the data as it moves through these business processes. My team has had a good experience with Cosmos DB. We have found that it is easy to interact with and use to query our application's data. We also use Cosmos DB in conjunction with other services in Azure like Service Bus, .NET APIs, and Azure Functions. I personally have utilized the Azure Cosmos DB Python SDK to perform queries and updates on data at CarMax. In my previous presentation with your meetup, I presented how we utilize Python scripts to automate interactions with Cosmos DB. The Python SDK provides a great way to easily interact with the data.
Thank you, CarMax and Andrew Evans. It's really interesting to see how they interact with data to improve their business. And to me, it's always fun to hear how customers are implementing integration with other Azure services and Azure Cosmos DB. And personally, I'm a big fan of Python developing language, so it was great to hear that they are using Python SDK. So folks, I want to remind you of the CTAs and everything that's going on right now. So please leave your comments in the YouTube chat, go to the resources page, and please leave us feedback using the evaluation form. And also, please use the hashtag Azure Cosmos DB Conf on social. You will be able to find all the talks on demand on our website. So, Patty, what's going to happen next?
Yeah, well, we had a great start to the conference, but now Dr. James Cadella from our team will show us how he is powering planet-scale AI with DiskANN. Let's take a look.
Yep.
Hey, everyone. I'm James Cadella. I'm a product manager in Azure Cosmos DB. Today, we're going to talk about how Microsoft powers semantic similarity search in some of the largest applications in the world using Microsoft DiskANN, a unique vector index that was developed right here at Microsoft. Now, before we get started, let's have a quick recap on what approximate nearest neighbor search is with vector search. So imagine that you have a database with hundreds of thousands or even billions of documents, and you create vector embeddings or representations of these data using a AI model like one from Azure OpenAI. Then your data set's primed to do vector similarity search, where you can have a query or a user question, and you can conduct similarity search against all those vector points to find the documents that are most similar to that question. So traditionally, you might want to do an exact search and search over all documents in the database, but this becomes really slow and intractable at scale. Instead, we use approximate methods and approximate nearest neighbor search and make a trade-off between the recall or accuracy and the speed of the search. Now, in Microsoft, there's a lot of really unique sort of scenarios, right? There's between the cloud environments or cloud applications from web search and ads and recommendations to enterprise scale email search and Outlook to document search and even edge applications like Windows Copilot. There's a variety of different index sizes. And that means that we have to be able to search efficiently no matter what the size or scale of the application or the use case is. Many of these applications also experience tons and tons of updates, so insertions or deletions of vectors into the vector index itself. And so we need a solution that's able to provide robust results and high accuracy results, even though there's modifications to the index itself. And finally, we need to be able to have really low latency search and handle high throughputs for the scale of these massively popular applications. And so traditionally, this has been a challenge for a lot of vector indexing technologies. The demands inside Microsoft spurred the need for a new type of vector index, and this started the DiskANN project. And DiskANN aims to solve multiple problems. The first is that traditional in-memory vector indexes tend to be expensive at scale because they need a lot of memory. DiskANN leverages compressed vectors that are stored in memory, but then uncompressed vectors on a graph data structure on high-speed SSDs to be able to do cost-effective vector search at any scale. The second problem is a lot of updates, insertions, modifications, and deletions to the vector index tend to make the performance degrade. That is, the accuracy can degrade over time, and so typically require a full index rebuild, which can also be computationally expensive and take time. The third problem is most vector indexes are not designed for filtered or hybrid queries, and so this could result in low recall or high query complexity or latencies. In comes Microsoft DiskANN. As I mentioned, it's a technology that was developed at Microsoft Research, and we're really excited that it's in Azure Cosmos DB as generally available for our vector indexing and search capabilities. The way it works is when you insert vectors in Azure Cosmos DB, we compress the vectors through product quantization, and these compressed vectors are kept in RAM of the Cosmos DB backend for fast access. The uncompressed vectors are used to create a complex graph data structure. These uncompressed vectors and the graph are stored on high-speed SSDs, which make up the backbone of the Azure Cosmos DB architecture. There are algorithms in DiskANN that make it really efficient at building the graph and also pruning the graph so it's very easy and cost-effective to search and has fast convergence of search. So combined, this makes vector search in Azure Cosmos DB very, very cost-effective. It leverages the unlimited scale capacity of Cosmos DB as well to provide low latency, robust vector search at scale. Now, Azure Cosmos DB is actually very well suited for vector search scenarios, right? It offers very flexible data modeling, right? So it's a NoSQL database, so you don't have to worry about a fixed schema. And we have tons of customers that are storing chat history, agentic memories, user interactions, but also e-commerce data or transactional data, operational data that's scanned from PDFs and images of the sort of operational data that comes from other applications. So there's really a lot of flexibility there. Furthermore, Azure Cosmos DB for NoSQL is enterprise ready. It features high elasticity and hyperscale, 5 nines of availability, low latency point reads and writes, continuous backup and restore for disaster recovery, multi-region and geo-replication, and also all the security features that you've come to know and love from Azure, such as virtual networks, customer managed keys, and RBAC policies. Cosmos DB also features a lot of usability and functional deployment methods that make it really powerful for any application that you develop, from a serverless model, so pay as you go or pay as you use, to a provision model with instant and dynamic autoscale capabilities. It also features many levels of built-in multi-tenancy, a SQL-like query language that's very powerful for getting the data that you want, and also offers multiple consistency levels. So combined, Azure Cosmos DB for NoSQL really is the best vector store for any of your AI application needs. Being able to store your vector index and your vectors together with your original data is a game changer. It removes the need to ETL your metadata into a dedicated vector database. You can keep your vectors and your data together, and it will simplify your application architecture and reduce your costs. Because of the flexibility of Cosmos DB's query syntax, you can add any query filters that you'd like that are supported in the Cosmos DB SQL syntax to your vector searches. So you can perform filtered vector search at any scale. We also offer multiple vector indexing options, from flat for exact search, quantized flat, so exact search on compressed vectors, and then finally the DiskANN index, which is really great for applications at scale. And we have thousands of customers today building a diverse range of scenarios, all powered by their data stored in Azure Cosmos DB. Storing operational and vector data together, as I already mentioned, is a huge value proposition for these customers. Built on top of this, many customers do retrieval-augmented generation, leveraging vector similarity search in Cosmos DB natively. Cosmos DB is also very popular as a conversational history store for agentic memories, for conversational context, and for LLM optimizations that you can use later on. Semantic caching builds on these two concepts, where you're storing conversational histories in Cosmos DB, and you can leverage previous responses from the large language model, doing a simple vector search rather than feeding more data to the large language model. This saves you in token consumption costs, so API calls to your large language model, which reduce overall cost and can save on the latency in your applications. And of course, all of these are very applicable to AI agents as well. Multi-agent scenarios need to retrieve data, need to store data, need to save a checkpoint or statefulness of the agent of the agents and the agentic applications. So Cosmos DB is a great storage layer for these transactional workloads, as well as for retrieval-augmented generation. Now, let's take a look at some examples of vector search in practice in Cosmos DB. So executing a vector search in Cosmos DB is really simple. As I mentioned, vector search is part of our query syntax, right? So performing a simple vector search is pretty easy. In this example query here, I'm selecting the top 10 most similar documents. I'm projecting a name field. I'm also projecting the vector similarity score and I'm giving as scores. So I'm giving scores and alias from C for my container. And I'm ordering by vector distance. So the order by vector distance is really important. This sorts the results in order of the similarity score from most similar at the top to least similar down below. If I want to do a filtered vector search, I can just add a where clause, just as I would in any other query. It's just that simple. I could even do customized search, leveraging DiskANN. Right, so I could, in this example, select the top 10 documents, and I'm going to project all properties of those documents. I'll add a filter as well. And this time I'm saying order by vector distance, and I'm giving the property that contains the vectors of my documents. I'm also giving the query vector, the thing I want to compare against. I'm saying false here, so false or true. False means that I will use the vector index, and true means I want an exact search. And then in this object here, defining a search list size multiplier. So this is a hyperparameter of my search. Basically, if I want my search to execute faster, I can lower this number. If I want my search to be more accurate, I can increase this number. And this finds more candidate vectors in the vector search itself. And so there's that trade-off, right? Just in any approximate nearest neighbor search, there's always a trade-off between latency and accuracy. So this is a really easy parameter for me to tune if I want a little bit more accuracy in my search, or maybe a little bit lower latency in my searches as well. Now, let's take a look at some numbers. So these charts show query latency and the RU charges for vector search on the Wikipedia Cohere embeddings dataset, right? So these are 768 dimensional vector embeddings that are created from the Cohere embeddings model. And on the left, we can see the latency, so milliseconds on the y-axis, and we can see the P50, P95, and P99 latencies here. So we can see different scenarios as well. We can see for 100,000 vectors, 1 million vectors, and 10 million vectors. So what's really interesting is we can see that the vector search is actually really nicely bounded, right? The latency is quite low. 10 million vectors in under 40 milliseconds, that's really amazing. On the right-hand side, we can see the corresponding request unit charges for executing a vector search. So we, at the P99 level, we have 100,000 vectors. A search on this costs about 30 RUs. And at the 10 million scale, it costs about a little over 70 RUs, right? So this is really amazing. We're going like 100 times more vectors that we're searching against. And yet the query cost only practically doubles, a little bit more than doubles, right? So this is really amazing. We can be really robust against very large scale vector searches, right? Because of the efficiency of DiskANN and the Cosmos DB architecture. Okay, let's take a look at some of the costs for this scenario. So imagine that you're inserting 10 million vectors of 768 dimensions into Azure Cosmos DB for NoSQL serverless. Then we're going to perform 1 million vector searches on this data. So the insertions of these vectors at 25 cents per 1 million RUs in the serverless model, and at a cost of 65 request units per insert, brings us to about $163 to upload all our data into Cosmos DB. Our storage cost, 25 cents per gigabyte per month, amount to about $23 per month. Then we conduct 1 million vector searches at about 60 RUs per search. This is roughly $15 for a total cost of around $201. That's incredibly cheap for vector search on Azure Cosmos DB with all the great enterprise-ready features that you get in a globally distributed database like Azure Cosmos DB. Let's see how this scales also. So here we have some plots on vector search from the MS Turing dataset. On the left-hand column, we have a scale of 1 billion vectors. And in the right-hand column, we have a scale of 100 million vectors. The top charts show latency, and the bottom charts show request units. And what we can do is we can see the latency on the server side in blue, or on the client side in green, on a spectrum of different scenarios where we're increasing L search. So this is that search list size multiplier I mentioned, right? So we're basically changing this to get higher recall at every step. So we can see that L search is 50, so relatively fast. We can see that the P99 latency on a billion vectors is under 50 milliseconds on the Cosmos DB backend, maybe around like 75, 80 milliseconds and on the client side. That's really, really fast for a billion vectors, incredible. Now, as we increase L search, we want to increase the accuracy. We can see that the latency also increases. But even at an L search of 200, which gives us a recall of nearly 94%, we still have our P99 server-side latency of under 100 milliseconds and our client-side latency as at around 140 milliseconds. That's super, super fast for vector search on a billion vector scale. And we have even more optimizations in the pipeline to bring those latencies down even further. We're really excited. Okay, so speaking of optimizations and new features, what's actually coming next? So we have performance improvements that are continuously rolling out to both DiskANN and the Cosmos DB backend to make your vector searches at scale even more cost-effective and faster. We're also giving you the ability to configure and change your vector indexes so you can do experimentation on what's right for your unique scenario, or you can modify it as your scenario scales. Coming soon, we're also launching what we're calling sharded DiskANN. This is really powerful. This allows you to create essentially unique vector indexes, so a unique DiskANN graph, for every property value of a document. So imagine that you have maybe a tenant ID specified as your shard key, or a particular category. Then you can isolate your vector search to just that category, or just that tenant. This makes the vector search much faster, more cost-effective, and also have higher accuracy. We're soon also launching filter DiskANN, which leverages new algorithms for improving vector search with query filters to make them faster and more cost-effective. You may also already know that in Cosmos DB, in addition to vector search, we also have full text search and ranking that allows you to search using a full text index for keywords and terms. We're soon adding a lot more features to this, and we're really excited that we're going to be announcing the general availability of full text search and ranking in Azure Cosmos DB at the Microsoft Build conference at the end of May. So we're really excited. There's going to be some really great new features that are coming along with it. So join us on Microsoft Build to learn more about that. We also have hybrid search in Azure Cosmos DB. So this is a combination of the vector similarity search and the full text scoring to bring you even more relevant search results. Again, it's really easy to execute in our query language. And this is also going to be generally available at the Microsoft Build 2025 conference at the end of May. We're also excited to be teaming up with the Microsoft Logic Apps team, right? So everybody knows Logic Apps, a very powerful resource in Azure for these workflows that you want to operate continuously with very low latency. Well, we're taking it to the next level by building templates that allow you to do document ingestion and processing. So essentially being able to do OCR and extract information from documents in blob storage or on SharePoint, process the data, chunk it, create vector embeddings from those chunks, and then insert them into Azure Cosmos DB for vector and full text search. This is going to be really powerful. Any operational data that you have in blob storage or SharePoint, you can be rest assured that it will be searchable in Azure Cosmos DB and stored there securely. Now, you may be wondering how you can get started with vector search, or where can you go for some samples? Well, the good news is we have a fantastic samples gallery. If you go to aka.ms/azurecosmosdb/gallery/AI, you can get started and take a look at our samples gallery that's filtered just for generative AI scenarios and samples. And you can find everything from chat examples of managing chat history in Cosmos to managing vector search in RAG, and even multi-agent applications with examples in Swarm, LangGraph, and Semantic Kernel. And if you've never used Cosmos DB before, you can get started from free. Just check out aka.ms/trycosmos, and you can get started on a lifetime free tier account. And you can do vector search on that free tier account as well. So really a lot of great options for you to get started and to use Azure Cosmos DB for your AI applications.
Thank you, James. It's always fun to listen to James' presentations about vector search. And now, Justine Kochi from our team is going to do a deep dive into the change feed. Let's take a look.
Hi, I'm Justine Kochi, a program manager on the Cosmos DB team, and I'm excited to talk to you about change feed today. Change feed is a persistent record of changes to items in a container in the order that they occurred. It's commonly used for patterns like event sourcing, auditing, or data movement, whether that be between containers in Cosmos DB or to downstream systems. The change feed offers different features depending on the mode that you read it in. One mode is latest version. In this mode, you can read the latest create or update for each item in your container. This mode has infinite retention, meaning you can read changes all the way from the beginning of your container. The next mode is all versions and delete. Here, you can get every create, update, and delete operation for every item, including TTL expiration. In this mode, if you have two updates to the same item in between change feed reads, the next time you read change feed, you'll see the update for both of those items, rather than just seeing the latest update. Changes in this mode are retained for the continuous backup period of the account, which means you can't read from the beginning of the feed, but you can read anything that happened within that retention window. For containers that are very active and have a lot of changes coming in, change feed is able to be parallelized across partitions so that you can read your changes even faster and ensure that you're keeping up with the volume of changes to your container. Let's imagine we have a Cosmos DB container with 3 physical partitions. This container is partitioned by city. I can create 3 change feed workers to process changes from each partition independently. That way, when updates come in for various partitions, each change feed worker gets an ordered list of changes for the partition that it owns. Now, managing these partitions and workers can be a bit challenging, so there's several different ways to read change feed that help you manage this. The first is change feed processor. Change feed processor gives you control over how you read the change feed and offers configuration options for things like the poll interval for how frequently you're checking for changes. It doesn't have the complexity of needing to manage checkpointing, error handling, or scaling across change feed workers as your container grows. All of that is handled for you automatically with the change feed processor. Azure Functions is a hosted option for the change feed processor, and it's one of the easiest ways to get started using change feed. There's also the change feed poll model. The poll model gives you the most control over how and when you read the change feed. However, it can be complex for some scenarios. Let's imagine a real-world application in the retail space. I have some business requirements. I want to create a fulfillment system that helps me track orders happening for my business. I also want to be able to coordinate order status updates across my microservice components for shipping, payments, and delivery. Let's see how the change feed processor can help us fulfill both of these requirements. I'm going to switch over to Visual Studio, where I have a console app running. You'll notice the first thing I do is initialize my Cosmos client. The Cosmos client is the entry point for your Cosmos DB account and helps you communicate with all of the containers and data in your account. Notice I'm authenticating with the default Azure credential, which uses Microsoft Entra ID authentication and removes the dependency on passwords. Once I have my client, I can actually create my change feed processor and create connections to 2 containers. The first container is my monitor container. This is the container that I will be monitoring for changes, and in my scenario, is my orders container. I also have a lease container. The lease container helps the change-feed processor maintain state for processing changes. You'll see one lease per physical partition, and this is how we can manage checkpointing and the order of changes that have been processed for each partition. Now, notice I'm creating my builder with all versions and deletes. For this application, I'm using all versions and deletes change feed mode to make sure that I get every order status update for my application. Once I've configured that, I can go ahead and start the processor to begin reading my changes. Now, one more thing to note is the handle changes async function. Handle changes async is called every time a batch of changes is delivered into the change feed. In this example, I'm going to loop through every order that I received and print out some metadata for the order. So let's go ahead and see what this looks like. I have my change feed processor application already running, and I also have the Azure portal pulled up with Data Explorer. This is my orders container, and I have a bunch of my orders listed here. Now, if I were to simulate one of my microservices making updates to this data, let's see the status goes from ordered to shipped, and we update this. We can see the change feed processor will automatically pick up this change and print our new order status into the console. Thank you so much. And if you're interested in using ChangeFeed, get started by checking out aka.ms/changefeed.
Yeah. Wow. Thank you, Justine. It was really cool to see how ChangeFeeds enable real-time event-driven applications, powering everything from personalized retail to instant insights. It's a great example of Azure Cosmos DB's power in operational workloads that need to scale and react fast.
Definitely one of my favorite use cases for Azure Cosmos DB. By the way, Patty, we have some social media posts here, and let's take a look at this one from Brian. He's currently following hashtag Azure Cosmos DB Conf, and even encouraging people to join the live stream, sharing the link. Pretty cool setup. Yeah. Laptop and monitor.
Thank you, Brian. And as always, please continue to drop in chats on our YouTube stream. Check out our resources page and our evaluation form.
Okay, so I just mentioned that the real-time apps is one of my favorite use cases, but so is this one too. Next, we are heading into the world of Gen AI apps and intelligent agents, and we learn how to build a rack-based retail copilot with Azure AI Foundry. Let's take a look.
Hello, my name is Nithya Narasimhan. I'm a senior AI advocate on the developer relations team at Microsoft, and I'm really excited to be here today to take you on a developer journey as we build a RAG-based retail copilot, code first, on Azure AI Foundry. Now, this is a shortened form of a talk that we've been taking out on the AI Tour as a 75-minute workshop and skilled thousands of developers. And we did it by deconstructing Contoso Chat. If you have a second, go check out that the QR code or the URL, start the sample or fork it, and go check it out after this talk and see if you can explore it by yourself. But today, I'm going to split this talk into 3 sections. First, we're going to spend some time knowing what Contoso Chat is, how it's architected, and how we should go about building it. The meat of this talk will then focus on interactive demos and exploration of the codebase to actually go through that workflow. And finally, I'll leave a little bit of time for us to think about how you can then use the sample as a sandbox to go explore ideas for Azure Cosmos DB features like vector search. So let's get started by talking about the application scenario. What exactly is Contoso Chat? So you might actually be familiar with this web app that you see on the right side. This is Contoso Outdoors, an enterprise retailer that sells camping and hiking equipment. Contoso Chat is their customer support chat AI. And when they built it, they had 4 requirements in mind. First, they wanted to make sure that it was conversational. Their customers should be able to come to this chat site, to the website, and chat with the website about what products are available in natural language. Second, the responses need to be grounded. So if a user asks, what should I buy for a trip to Andalusia? They should get back responses featuring products that are in that catalog. Third, it needs to be contextual. What that means is it needs to understand that there's a chat history, that the consumer might have previous purchases that are relevant to the query, and so on. And most important of all, it needs to be safe. We all know there are techniques like jailbreaking where people try to use prompts to change the behavior of a chat AI in ways that you didn't intend. So one of the things we want to make sure is we can protect against jailbreaking, but also take the time we need to make sure that the responses are of good quality and safety. So as you can see here, with our demo, when you build this app, it will have built-in guardrails to prevent things like jailbreaking. Let's see how we build that. But before we do, let's take a look at what our data sources are. This is Cosmos DB Conf after all. So we have two kinds of data sources, and we did this on purpose, so you can actually go explore both structured and unstructured data. A product catalog sits in Azure AI Search. It has structured data in CSV format. Now, if you fork the repo, you can go into the data folder and look at the product info subfolder, and you will find that list of products. You have 20 product items, a good healthy sample, 8 product categories, and columns like price, name, brand, description as metadata. We also have a second set of data. This is unstructured data in JSON format, and this represents our customer data. We have 12 customer profiles. Again, you can go into the data folder under customer info. We have 12 customer profiles. Each profile gives you a little bit of information about the customer and has 2 to 3 purchase orders that they've made from the site as history. So with this data, we now want to build a chat AI grounded in this data. How do we do it? The answer is retrieval-augmented generation, or RAG. I'm not going to go into too much detail because we're all probably very familiar with this design pattern. But let's take a quick look at the flow so we understand how this maps to our architecture later. So typically, when a user goes to a model, a large language hosted model, and asks a question, if it goes directly to the model, they're getting back answers that are based on publicly available information. So if I ask, recommend me a tent, it's going to come back with a publicly available one. But if I want to ground it in my data, we use retrieval-augmented generation. We take the query and send it to an information retrieval service, which can vectorize the query, find matching results, and return that as knowledge as part of the retrieval step. We then augment that original question to create an enhanced model prompt that contains the question as well as this retrieved knowledge, along with instructions, which we then feed to the large language model, allowing it to generate the response, which magically is now grounded in that data. So how does this map to our architecture? This is the Contoso chat architecture. And you can almost see RAG in play. The user input comes in. Our Contoso chat AI is hosted on Azure Container Apps. A request comes in through this. It gets fed to a workflow, starting with an Azure OpenAI service for embeddings, which takes the vectorized query and sends it to search. Can also send the query to Cosmos DB, get back knowledge, enhance the prompt, feed it back to the chat completions method, which gets the response, which goes back out. Simple, right? Not so fast. Building this is actually really complicated. We have seen a paradigm shift. You might have heard the term Gen AI Ops, where the application lifecycle is now complicated by the fact that our inputs and outputs are in natural language, which is non-deterministic. So when we think about building this, we actually have a 3-phase approach. First is ideation, where we have to select the model that we want to use and maybe use a prompt, a test prompt, to test it out and see if it can do what we want it to do for our application. Once we've decided that's the model for us, we move to the next phase, building and augmenting. That's a place where we spend a lot of time as developers. We enhance that prompt. We potentially do things like retrieval-augmented generation, adding data access, orchestrating the workflows. And then we do things like evaluation to test that those responses are actually of good quality and act in a safe manner across diverse inputs. And when we're ready, we move to the final stage of operationalization, where we make this chat AI hosted, available as an API endpoint that can be accessed by real-world apps. But if you look under the covers, there's a lot that's happening. How do we do all of this? This is where Azure AI Foundry can help. And today we're going to look at how you can use the Azure AI Foundry platform to go from catalog to code to cloud. It provides you the tools, the services, and the models that you need to build your generative AI application in a streamlined manner. So with that, let's actually dive in and look at the sample and try to figure out how we build this step by step. The first thing we're going to do is look at a quick start. How do we jumpstart our development process, given that we have an open source sample? And we're going to do this by looking at what we call AI app templates. You can go to that QR code or to that link to actually visit the site that I'm going to show you in just a minute. It looks something like this. And let me just quickly make sure that my code space is still alive. Yep. So the Azure AI template site looks something like this. What it is a bunch of pre-made open source samples that have architectural designs and code bases that you can launch with a single command that will both provision and deploy the resources and give you a running application that you can use for exploration and extension. It uses infrastructure as code. So basically, your provisioning is defined through bicep or ARM files. So in this, to find Contoso chat, simply go and pick the language, Python, and the two data types that we're using, the databases we're using is Azure AI Search for the product catalog data and Azure Cosmos DB for customer data. And you'll find that there's only one template that does this. Click on this template, and you should get to a screen like this. This is where you can find out more details about what that app is doing. So in this case, you can get to see the example that I showed you, the architecture diagram, and know a little bit about the services that we're using. But you can go seamlessly from here to actually start using the template. And I encourage you to do that. Click open in GitHub Codespaces, and you will get a link like this that will take you to a code space. And it should actually, now this is going to the main one, but there is a link that you can do to take care of a pre-build. And we'll put that for you in just a second. If you click that, you will then end up getting a code space like this. So let's go back and see what that does. If you actually go click on that link and get this far, you have now completed the setup. You've got yourself a Codespaces environment, and this reflects configuration as code. So all the tools, all the dependencies you need are already installed for you, and you can immediately get started building. In this, what you are now going to do is AZD up. Now, I've already done this for you, but if you look at the instructions here, it'll actually tell you how to go through those two steps for getting started, and you can follow along. In my case, I've already started that and run AZD up. So what does AZD up do? If you want to actually go into the step-by-step, I encourage you to go to this site, which has a self-guided workshop that I'll show you later on, where you can take these steps on your own. But all I will tell you for now is that when you run AZD up, it's going to complete the provisioning of those resources on the backend and deploy the first version of your application and make sure you can now have an Azure AI project ready for you to go play with. So let's take a look at what that looks like. So as I mentioned, I already ran this prior to joining this call. So this is what my provisioned application looks like. Note that I have a resource group with all the resources deployed, and you can see that there's an Azure AI Hub, an Azure AI project, and Azure AI services that come from the Azure AI Foundry. I have a Cosmos DB account. I can actually click on this and go check out what's available there, and we'll do that in a second. And I can actually go in and look at the deployed container apps. So I'm going to go ahead and open that up here. So you can go into the Cosmos DB account, open up the Data Explorer, and you should see that the records that we had for customers are already in there. So give it just a second, and there you go. So you can see that the data is already uploaded. Similarly, we can go into the deployed container apps, and you'll see that we have a first version of our AI already deployed. We can go to the Swagger endpoint, and if you want to test the application, we can test it here, and we'll think about that later. So now you know, with just a few minutes and a few clicks, you are able to set up your development environment and deploy your resources. What's next? Now it's time for you to ideate. So let's go back and look at our Azure AI environment. When we deployed these resources, we also set up an Azure AI Hub and an Azure AI resource, a project resource. This is that resource. So if I look at my project, I will notice that I actually have, as intended in the architecture, I have deployed 3 models out of the box. First is a chat completions model. In this case, we're using GPT-4o Mini. Second is an embeddings model. In this case, we're using text embedding Ada 002. And third will be an evaluation model. We're using GPT-4. So let me just wait a couple of minutes for this to settle down. All right. Now you can actually go in and check out a deployed model. Now remember that this deployed model is effectively just the large language model, and I can open it in a playground and start my ideation right here if I so choose. So I already went ahead and did a really simple test where I put in the model instructions and context, and I gave it a simple query. Tell me about your camping stuffs. And you'll notice that when I ran that query, it gives me a very generic answer. It's not grounded in my data. So when we ideate in the playground, that result is not grounded in our data. In order for us to do that, we now need to orchestrate the flow, connecting this to various resources and building out that prompt template. Let's see how we do that next. To do this, we're going to go back over to code spaces and start looking at the code. So remember that when we ran AZD up, we provisioned the infrastructure, but in doing that, we also have our development environment set up. Now, I'm not going to show you, but what it does is it actually sets up an environment variable for you, or .env file, that has all the environment variables you need to actually connect to the backend infrastructure. So now we'll start our ideation process. Remember, I told you we have a step-by-step workshop. If you do want to follow along, the URL is in the left side, in this QR code. But the workshop instructions can also be found online, and they look something like this. You want to go ahead and do the self-guided setup. And when you're done, what we're doing now is going through the ideate process. So what exactly is happening here? We notice that we have a model deployed, but it's not grounded in our data. So we want to start kind of using that model, configuring it, and then building a prompt template. To do this, we're going to use a technology called Prompty. So what is Prompty? I'm going to start by actually showing you a basic Prompty file that you see here. When you install this app, you will actually get a built-in extension. There's the Prompty extension right there. And it comes with tools that helps you create. You can do a new Prompty and get this basic Prompty that you see right here. That helps you create this asset, a prompt asset, and provides you a runtime that you can test in right in VS Code. Effectively, you've brought your playground from Foundry into your development environment. So what does a Prompty look like? The basic Prompty that gets set up for you will look something like this. It'll basically have a metadata, a front matter area that defines the model and the configuration parameters. It'll have a sample input that you can use for testing, and it'll have beneath it a prompt template. You can see the system context, and it has some basic information. Now, this is just a standard starter Prompty that is created for you. Because we're sitting inside VS Code, we can actually run it directly here. So you'll notice that when I run this, it fails. And this is expected because what happened is that we don't actually have the setup with the right endpoints. Or we don't have it set up with the right deployment. It's got the wrong value. So if you go through our workshop, what we do is we actually then fix that by providing it the name of the right deployment and have the endpoint set up to use the environment variables we've already created. So now let's go ahead and run this again. So this is equivalent to iteration. You took that chat Prompty, and now you fix the issues that it had, and you can run it. So this is version 1. So when I run it this time, let's try this again. All right, if you can see the results here, now staying inside VS Code, I was able to run this Prompty, configure to talk to the model, and it used this as the system context and used this as my instructions and answered this question, which is, what can you tell me about your tents? And as you can see, it followed the instructions. I'm helping this person use their name to address them. Hi, Nithya. Here is the answer. It's still not grounded in my data. But this is how we can start iterating. The next step we're going to do is we're going to take this sample input and move it into a file. Now you're beginning to see data that has the shape of the kind of data that you would actually find in Cosmos DB. Here is my customer unstructured data. That's my customer input. There are the orders. I can now go ahead and iterate on that chat promptee to use this file as the data. Now, by doing this, I've immediately moved away. I've started shaping the data. So now by having it take the inputs from a JSON file, I can continue to test my promptee templates, but know that down the line, I can then connect to an API to get that JSON data dynamically during my orchestration step. So here, my sample file is connected to a very simple customer record. I've now also enhanced my prompt template to use this information in meaningful ways. And I've given instructions for the model to answer the question grounded in this context. So if I run this now, note that I'm still taking data from a sample file, but it's beginning to respond to the way in which I am engineering my prompt template. In the next step, I can keep going. So we can kind of go through this whole thing if you like, but the next step, what we're going to do is we're really adding safety. So in this particular case, I'm going to look at this and say, all right, I'm going to change this to 2.json. Now, you'll see why in a minute. Chat2.json is a sample that actually puts a jailbreaking style input. So over here, all I've done is said, hey, is mine currently allowing me to kind of work with prompts that could jailbreak my content? So if I go back to where I was before and I try to use that input, you will notice that it will, in fact, allow it to say harmful things. So let's see if that just runs. There you go. So you'll notice that I asked it in that prompt to tell me about its rules and use bad emojis. And it did that because I didn't have any safety guardrails. But now when I move to the next iteration where I've put the safety guardrails in, if I now try to run this with the same input, you will notice that it will not allow it. So let's kind of wait till this is done. And it'll say, I'm sorry, John, I can't share this information. So this gives you kind of a really good sense for how we can start ideating right in the browser. And at the same time, we're using a sample of data that we would find in Cosmos DB later. But you're asking yourself, this is a promptee asset running in a VS Code runtime. How do I make this work in a code workflow? To do that, promptee actually has a built-in capability that will allow you to convert it to code. And so you will be able to get a Python version of the same code that you can then run to get the results that you want. With that, we kind of get to the end of our ideation. Now you've got yourself a sandbox where you can rapidly ideate on those ideas that you have until you get your prototype to where you want it to be, and you also know what that data looks like. The next step, and remember where we have the JSON file, when you write the orchestration code, once you've got it in Python, you can actually go ahead and replace the loading of the JSON file with calls to the different services you're getting this from. And if you go look at the source for this app, you'll find it in there. But wait, before we can actually make this available to the world at large, we need to make sure that the data, the responses are actually valid for a wide range of inputs. This is evaluation. LLM as a judge. Now, running this would take a really long time, but if you're interested, again, go check out the instructions. I went ahead and ran an evaluation ahead of time so you can see what the results would look like. So in here, if we look at our evaluation notebook, what evaluation does is it effectively allows you to teach a second AI how to grade the responses from a first AI using evaluation metrics like coherence, fluency, relevance, and groundedness. And we're interested in groundedness. So when you want to do that, you would basically, in this particular notebook, what you would do is first you would load up a set of sample test inputs, which you can find in this file as well. I mean, in the code base as well. And you will run them with your chat AI. which will answer all of them and give you back its results. You will then take these results to your grader AI, your evaluator, and ask it to grade these responses based on criteria that you have defined. And if you're familiar with Prompty, you can go ahead and look under the custom evaluators and see how you can literally write the prompt template that will be used by that evaluator AI or the LLM as a judge to grade those responses on a scale of 1 to 5. When you've completed that, you should then get back a result that looks something like this. And here you will see that what it has done is it has executed the evaluation notebook. So when we finish running the evaluation notebook, you will notice that at the bottom it gives you the metrics for the evaluation. And you can look at these to understand why your answers are graded a certain way and how you improve the quality of your responses. And with that, we come to the end of our end-to-end workflow. The only thing left for you to do is deploy. And AZD deploy allows you to deploy directly from your code base and update the deployment from the previous provisioning at any time. But let's go take a look at what that deployed endpoint looks like. This is the container app that gets deployed every time you run an AZD deploy. And you can now go ahead and ask it questions like, tell me about your camping steps. And the thing that you will notice here is that I'm giving it a customer ID of 1, is that now this chat AI, which is still using the model that we saw in the playground, because it now has the orchestration flow around it, will return responses that are grounded in your data. So with that, we come to the close of our really rapid overview of this end-to-end journey in GenAI to build a retail RAG-based copilot on Azure AI Foundry. There's a lot more nuance to this, and I encourage you to go check out the workshop and the sample. But I want to leave you with one more thing. This is a Cosmos DB conference. So in this, you saw how we were using Cosmos DB to store our customer data. You saw how we were using Prompty to kind of ideate with the shape of the data. And if you go look at the code base, you'll see that we finally do orchestrate it to talk to Cosmos DB to get that information in real time. But wait, we were doing our vector search on the product catalog in Azure AI Search. Cosmos DB now has these capabilities as well. How can we use this sample to explore that? I leave you with this as a challenge. Use the sample as a sandbox. Here is an example of what you can do. For instance, there is a really good tutorial in the Cosmos DB site on building a RAG chatbot with Azure Cosmos DB NoSQL API. And it's fairly easy for you to walk through that. First, you've got to go ahead and activate vector search in your Cosmos DB deployment inside Contoso Chat. And then you can walk through this. And I have a slightly older version of it I'm still working through, but you can walk through this and then effectively change the data in that sample to use the data in your JSON file. And when you do, you should be able to get yourself a demo where you can actually see responses in the Gradio app that's deployed. So over here, we now have a Gradio app from that particular sample that is talking to our Cosmos DB, to our Contoso Chat endpoint. When I say, tell me about what you know, it kind of gives me a response. And the only thing left for us to do now is to write the queries and enhance the vector search capabilities and test it out with evaluation. So with that, that was a really rapid overview of what we wanted to cover today. Thank you very much for listening. As I mentioned before, this is a workshop that you can find at the link that you see here. Try this out on your own. By the time you see this, there will probably be an additional segment that will walk through some of the Cosmos DB vector search capabilities as well. So look out for that. And with that, thank you very much. And I hope to see you all at Microsoft Build.
Hello, everyone. I'm Marius Höcker. I'm an AI and software engineer here at BBV Software Services in Zurich. And today I want to talk about AI agent orchestration. I want to show how and what is needed for AI agents to be able to communicate. I only have 5 minutes, so let's get started. So for the past 2 years, a colleague of mine and me, we've been building on a multi-agent system, solving various use cases with groups of AI agents. Because we quickly realized that the collection of AI agents is much more powerful than just one generalistic agent. Almost every task benefits from being split down into subtasks. Same applies to AI agents. An agent with one specific knowledge is easier to manage, less likely to drift away from its intended context, and therefore is also much more reliable. However, enabling agents to communicate with each other is not that easy. Initially, I thought they can just communicate over natural language or text because that's their common interface. But to orchestrate agents, there's much more that's needed. For example, an agent needs to know about the capabilities of the other agents. To illustrate how this can be managed efficiently, let's take a look on the Model Context Protocol proposed by Anthropic. This protocol uses servers and clients. Servers provide information like data, for example, weather data or company policies or news, and they can also execute action. Clients, typically large language models or LLM-powered applications, perform tasks requiring these data from the servers. So servers expose so-called tools, described by their functionalities, the required inputs, and the expected outputs. The client then can evaluate, based on the tool's description, which tool fits best for the achievement of their goal, and then can provide the required inputs. You might wonder, what has this to do with AI agents? Well, an agent can serve both roles. It can be server, but also client. For instance, an agent being tasked to answer a question about weather can dynamically call a tool from another agent who's exposing its weather tool, and therefore the other agent is then the server. Through this approach of exposing tool definitions, agents become accessible to one another. However, not all agent tasks are as simple to just be resolved by one single request. Often tasks are much more complex and need multiple agent tasks and specific conditions to be completed. Such task needs internal states to track the progress. For example, also OpenAI, in their most recent release, the Responses API, they also introduced a stateful API. This is how important the tracking of the progress is. So agent must understand the current cause context and the previous achievements by other agents. To handle this, we took inspiration from the LangChain's agent protocol, which organizes the interactions into tasks, into runs and threads. Runs represent task executions, and threads groups related tasks together. For example, a thread could be the booking of a holiday, and a run could be the booking of just a flight. Now, it also can happen that the agent needs more information for the completion of their task. For example, it needs to know whether additional baggage should be booked as well. In this case, it can make a human-in-the-loop request, and then the initial flight booking request and the human-in-the-loop request to ask whether additional baggage should be booked as well. All these belong then to the same run because the task is not completed yet. This is where we actually use Azure Cosmos database greatly. We use it to persist our internal states, so the run and thread context. And here we use the flexible schema, the real-time data consistency, and the global distribution. This ensures that our run and thread context are always instantly available for all the agents. And by the way, we also store our agent or tool definition in the Azure Cosmos database. But most important for us is to quickly adapting to new AI developments and easily experimenting with new approaches. And here we also use Azure Cosmos database because its flexible schema and the ease of use allows us this to be greatly flexible and try out new things. And now let me briefly broaden out the perspective. Currently, most companies using or building multi-agent systems only focus on their own agent. But I truly believe agents are much more powerful if they collaborate together with, but especially also across company boundaries. Since first mentioning a global ecosystem for agents over a year ago, this has been inspiring me all the way. I envision agents to be rented out to other companies and integrate in their system, negotiating about contracts and building together on joint projects. This is why I've closely followed AI agent protocols, continuously adapting our system with the help of Azure Cosmos Database, preparing us to be ready when one of these protocols becomes state-of-the-art. And with the recent announcement of OpenAI to support the Model Context Protocol, I believe this is the number one contestant. With that, I want to close. I provided here some more resources about different agent protocol approaches. And with that, I wish you all the best for the rest of the conference. Enjoy.
Thank you, Nitya and Marius. Really interesting stuff. I really loved the story about how to build a RAG-based Copilot experience, starting from the scenario to a quick start and then following the best practices to go from a prototype to production. And the AI agents topic is always very interesting. And I've always been wondering how these agents actually communicate with each other. And so now there is the Model Context Protocol, MCP protocol, which makes that possible. How about you, Patty? What did you like about the session?
I especially liked Nitya's workshop because I can essentially just, after the show, I can go in and get started. So I can't wait to do that.
Me neither. I need to get some hands-on experiences, right? Yeah. And by the way, let's go back to social media. So this time we have a social media post from Dennis. He's saying, tuned in and soaking up the insights at hashtag Azure Cosmos DB Conf, loving the innovations and real-world use cases being showcased. Yeah, it's been an amazing start for Azure Cosmos DB Conf, lots of insights, and please keep these comments coming. Use the YouTube chat and leave your comments, and also give us feedback using the evaluation form.
Yeah. And thank you, Dennis. Last year, we talked a lot about cost optimization and the release of dynamic scaling. And Simon Kofod is going to share about how Azure Cosmos DB is helping him do just that. Next, our friends at QVC are going to talk about building a centralized product data hub with Azure Cosmos DB. But first, let's hear how Mike Calvin, CTO of Connectify, is helping the world of gaming stay secure. Let's take a look.
My name is Mike Calvin. I'm the CTO at Connectify, and we build an anti-money laundering compliance platform for the gaming industry, ingesting player and transaction data from the largest casinos and gaming organizations in the country. I'm responsible for the entire technology team. I'm also the principal architect for our platform, and I wrote the first lines of code back in 2021 when we got started. We are using Azure Cosmos DB as our operational data store, ingesting millions of transactions a day into our platform, analyzing them for suspicious activity, and then assisting our customers with processing and filing government filings and whatnot on those transactions. So we have a very high throughput platform that we have to ingest high volumes of data very quickly into. And Cosmos DB has been an awesome solution for us to be able to scale out horizontally as needed and manage cost as well, scaling back down to smaller sizes when we're not ingesting that data from our clients. We've realized a ton of benefit from Cosmos DB, everything from the ultra high performance, single millisecond latency point reads from anywhere in the world, to hyper scalability. We've gone from a database that was measured in single digit gigabytes to multiple terabytes in less than about a year and a half's worth of time. So we've been able to scale very quickly on Cosmos, and we've had a huge developer impact, allowing us to build quickly without having to deal with schema changes and the complexities that relational databases introduce into operational systems. So it's made our developers faster, our deployments more reliable, and our platform as performant as it possibly could be.
Hello, my name is Simon, and I'm a lead software developer at Novo Nordisk, a 100-year-old Danish pharma company. Novo Nordisk has a lot of factories around the world. We have almost 100 factory lines, and the plan is to triple these over the next couple of years. So we are expanding a lot, and we need to keep that in mind when we are building software. So even though we have a predictable usage, then it's going to grow steadily over time. But what I'm here to talk about today is how our team uses Cosmos DB and how we have been able to reduce cost as a side effect of implementing new features in our line of business application. So first, I'm going to talk a little bit about our application. What is it used for? Who are the users? And what value does it bring? Then I'm going to tell you something about the evolution of the app from a simple POC to the full-scale solution we have today being used out of the factories. Then I'm going to go through the data modeling, the capacity mode, and then finally touch on the achievements that we have made. Okay, so Digital Checklist is a line of business application being used by the operators on the factory lines that I mentioned in the introduction. So the application helps the operators coordinate their work when they're doing a batch changeover. And a batch changeover is the process being done when we go from producing one product to another. So it could, for example, be on a packing line where we pack a product for Italy and then we pack a product for Spain. So the packing and labeling and everything is different. So we have to clear the line and clean it and make sure it's ready for the next batch. So this could, for example, be 6 operators that has to coordinate between maybe 50 and 100 different tasks. And as you can imagine, this is going to take a long time. And while the operators do their task, the line is standing still. And when the line is standing still, then we don't produce any products. So by making a digital solution that can coordinate all the tasks between the operators, we can actually reduce the total time it takes to do a batch changeover. But more importantly, we can also reduce the number of mistakes or deviations that might occur. So when we do these batch changeovers, a mistake or deviation could occur. And if it does, and if it's critical, then we might have to scrap the entire batch. That could be worth millions of dollars. So just to recap it, we have a simple app, and you can call it a checklist that contains some metadata and a list of tasks that the operators has to do during this batch changeover. And on the picture, you can see one of the operators using our app. And to the left, you can see a screenshot of the app. So it looks really simple, and that's the point, but there is actually a lot going on behind the scenes. So let me take you through the evolution of the app from a simple POC to the scalable app that we have today. So this diagram shows the original POC we made to prove the assumptions we had. That a digital solution can reduce the batch changeover and reduce the deviations. And the POC was actually very basic. So it just consisted of a Swift application, a REST API, and some metadata persisted in Postgres. So this was done in a simple way to reduce the development time and allow us to fail fast in case we couldn't prove the value. But as it turned out, and as I alluded to before, we could actually prove our assumptions. So we got to go ahead to build a production-grade solution that is both scalable, maintainable, and extendable. And even though the POC worked, it had some basic flaws. For example, the most obvious one is that the clients are polling the backend to get updates. So every 5 seconds, the app would ask the backend for the entire state of the batch changeover. So not only does this put a lot of load on the backend, it also doesn't scale. So you can imagine if we have 5,000 clients, then our backend would have a problem. So to fix this issue, we introduced Azure Web Pub/Sub. So instead of letting the clients poll the backend for updates, then the backend would simply just broadcast events to the clients whenever something happens. So that could, for example, be when the backend or when somebody completed the task, then it would just broadcast task completed to all the clients. And then at the time, Azure Web Pub/Sub did not have the reliable sub protocol. So all the events would have to. Can we do this slide again? Okay. So to fix this issue with polling, we introduced Azure Web Pub/Sub. So instead of letting the clients poll for updates, the backend would simply just broadcast events to the clients. For example, the backend would broadcast an event every time a task is completed. At the time, Azure Web PubSub did not have a reliable sub-protocol. So we could not really trust that the events would reach the clients or they would reach in the right order. So the clients would still have to call the backend to get the latest date every time they got an event. But it will still be fast enough to give the operators a real-time experience. So when an operator, for example, pushes task solved on the screen, then all the other operators would see it immediately. So even though this design was not optimal, the introduction of Azure Web PubSub and the publish-subscriber pattern would later on end up being a really big benefit for us in regards to Cosmos DB and the cost optimization. So the next iteration, and the one we have today, introduces Cosmos DB. So during the development of new features, we realized that our data fits very well into a NoSQL model where the data is denormalized. So our data structure in Postgres was almost over-engineered, and having a schema to maintain was kind of a pain. So we actually prefer the flexibility of having a schema-less structure, and we feel like it increases our development speed. And at the same time, Microsoft took out Azure Web PubSub reliable PubSub protocol as a preview. And that had a major impact on our Cosmos DB usage. Because now we could actually rely on messages getting to the client and in the right order. So instead of just sending events to the clients, we would just simply send the entire checklist state to every client. And because of this, we could also limit the number of operations that we would actually have to do towards the database. So you could imagine having 1,000 clients or maybe 5,000 clients. Then every time somebody completed a task, we will still only do one Cosmos DB operation. And then the backend would broadcast everything to the front end. So the data modeling. When we started out with Cosmos DB, we initially considered using Cosmos DB for Gremlin because all the tasks in the checklist have a specific order, and some of them are depending on other tasks. And also one of the benefits we saw of using Gremlin database or a graph database would be that we could use it to determine the most optimal task to perform next. But when we thought about it, we actually thought that maybe in the future, tasks wouldn't really be depending on each other. And maybe some tasks would not be performed by an operator. So we actually went away from this idea, and then we went with Cosmos DB for NoSQL instead. And initially, we thought that it would be a good idea to have each task in its own document, and then have a document with all the metadata about the checklist. And everything should just be grouped together in logic partitions with a shared partition key. But when we did some experiments, we actually found out that this model had a really high request unit consumption. And having all tasks in a single document would actually be much better. So that's what we ended up with, a single document that just represents an entire checklist and all the tasks involved in the checklist. So it's a better solution for us as developers because we can easily query the data, and a single document just contains all the information we need. And also it costs less request units to query one of these documents. This model has one drawback though, compared to having multiple small documents. There's a higher risk of getting concurrent updates on the document. So imagine two operators having to solve a task at the same time. So this could result in two concurrent patch operations on the document. So that could be a problem. So we just deal with it by using the etag attribute. And if there is a concurrency issue, then the backend just retries again. So the developers are happy, the performance is good, and the request units cost is actually pretty low. Next up, we have to choose the right capacity model. So the graph here shows our consumption of request units over a regular week. It might look a little bit spiky, but if you zoom in on a second interval, it's really not. So our estimate is that we would consume 2.5 million request units and use maybe 400,000 database operations per month. So of course, this is going to grow over time as we get more factory lines, and we have to keep that in mind. So we have three options for the capacity model. We can either choose manual provision throughput, auto-scaling, or serverless. So with manual provision throughput, it has a minimum of 400 request units per second, and that's equivalent to 1 billion request units per month. So that's way more than we need. And if we set the request units to 400 request units per second, then I think we would rarely hit the rate limit. And the rate limit happens if we exceed the provision throughput. And according to the Azure pricing calculator, this setup is going to cost us $24 per month. Then we have auto-scaling. So auto-scaling is actually really difficult to predict. And it's optimal if you have usage that changes a lot. But it can actually also be useful if you have consumption below 400 request units per second. And we estimated that maybe we could halve the cost by using auto-scaling, because if we set the maximum to 1,000 request units, then we could hope that it would actually scale down to maybe 100 request units per second. But again, I'm guessing here, and I have not really done the calculations on our existing usage. The final option is serverless. And serverless is a consumption-based plan, so you pay for the request units you consume. So our estimated consumption is 2.5 million request units per month, and that's actually less than $1 per month. So that's not a lot at all. And another advantage of serverless is that we would not hit the rate limit. So this just seems like a perfect choice for us. And in fact, if we look at our bill, so this is our latest bill, and I'm sorry, the prices are in Danish kroner, but I think you can see what's going on here. So we pay around 70 danske øre per month. So this is for all the request units, it's for the data storage, it's for the network traffic, and it's for backup. So that's really cheap. So just to sum it up, as I mentioned, we have done all these changes either to improve performance or implement new features. Nothing here has been made for cost optimization except to choose the capacity mode. But we actually ended up with a pretty good reduction anyway. So we went from a Postgres database that will set us back $240 per month to Cosmos DB that costs less than $1 per month. And we can actually multiply this saving by 4 because we have 4 environments. We have a dev environment, test, and then a staging, and then a production environment. And then a little fun fact. Actually, an Azure metric alert is also 10 cents per month, and that's mind-blowing. So we are actually paying the same for our Cosmos DB database as we would be paying for just one metric alert. So to monitor the request units would actually double our database cost. And then a really interesting bonus and add-on when you're using Cosmos DB and the serverless option. So Azure Database for Postgres Flexible Server consumes a lot of CO2, and the Cosmos DB serverless does not. So we can actually reduce our carbon footprint by 22% by deleting or getting rid of the Postgres database. It's not like we are talking tons of CO2 here. It's kilos, but I still think it's not a lot, but I think it's something anyway. Okay, so this is the key takeaway from today. And I know it might be a hot take because I've talked with a lot of developers and architects that says that Cosmos DB is expensive and it's reason enough to stay away. But I think it really depends. So if you have a use case and an architecture that enables you to control how you interact with the database, then the serverless model is actually really inexpensive. And could we have done something different, like using a cache? Yeah, I think we could. I think we could have done many different things. And we could probably also host the Postgres database in another way. We are using the general purpose instance of the Postgres database, but maybe you could scale it down to something smaller. But I still think it's not going to get us down to 10 cents per month. So we are actually running this production-grade line of business application on many factory lines. It's scalable, it's extremely fast, and we only pay less than $1 per month for the database. So that's all I had for you today. Thank you for sticking around to the end of the presentation, and enjoy the rest of the Cosmos DB conference.
Hi, I'm Senthil Chandrasuryan. I'm a solutions architect at QVC Group. Today I'm going to be talking about a product data hub that we have built within QVC using Azure Cosmos DB, some of our architecture, and how we plan to use some of the things in the future as well. So just a brief about QVC, though, for those who don't know, we are a telemarketing company. We sell our products through the television channels. We have like about 12 channels on QVC. We are also HSN. We sell our products through HSN as well. We are in a lot of different markets, including US, Germany, Japan, and other places. So as a retailer who sells our products, right? So products are basically like the product data becomes essentially like our central data source that's needed for all of our operations. So it forms the basis of our selling process, and we need to really provide like a good real time visibility for our different product attributes like the core product attributes, inventory, pricing, and promotion across various different sales channels for marketing and a lot of other purposes. So we have a very unique use case for handling our product data. Some of the information is listed out in this slide, but what we needed is a very reliable, high performant system that can provide us product information that can be shared across different channels, and make it available for us really quickly. So this gives us like a view of how we have laid out our product data using Cosmos DB. If you look at the diagram that's shown on the right hand side, the QVC product data hub, which is created using Cosmos, becomes a central hub, and at the top you will see our various channels. We are actually branching out into streaming platforms. We are branching out into social selling platforms, and basically for all of the product data needs that we have across our television channels, our social channels, streaming channels, and marketing, like search and recommendations, all of that's like kind of getting provided using our product data hub that's created using Cosmos. At the bottom of it, what you will see is that we send all of this information from our on-prem systems using like a host of services like that are available in Azure. We use things like Service Bus, topic subscriptions, Data Factory, along with the host of Azure Functions, Logic Apps, and our own services that are running in Azure AKS to push the data over to Cosmos, and from there make it available everywhere. Why did we choose Cosmos? Mainly for the reasons that we have listed out over here. It has an excellent global distribution, global replication across like various regions. It provides us with a very low latency reach, which is very critical for since that data is going to be made available in all of these different channels. It provides schema flexibility. We can tap into change feed, publish data out. It supports event sourcing, and then the Cosmos DB is also like a source, is the place where we store our event sourcing data, and it has excellent connectivity to Azure services. And our plan is to expand our services in Azure. That's one of the reasons for why we are using Cosmos, and we have been extremely happy with all the capabilities that we get out of Cosmos. And we plan to expand our product data hub functionality by making Cosmos as our central place where we store that information. So from there, where do we want to move towards, right? So one of the things that we want to kind of move towards is expanding our AI capabilities. We do this currently using like various third party solutions, but what we want to do is we want to start building these capabilities using Azure OpenAI, and then basically kind of dive into some of these areas, like creating product descriptions based on images and videos, creating personalized browsing experience using information that's coming from analytics, and loading that into snaps and creating like a personalized experience, bot that can answer questions regarding our products when the user visits our website. And then ultimate goal is to provide like a AI guided shopping experience by taking all of this information and driving the information that we have within Cosmos and basically tying all of these up together and provide a guided shopping experience for all of our users. Thanks so much for your time, and thanks for sharing. Thanks for giving me the time to share our vision of creating the QVC product data hub using Cosmos. Thanks once again. Bye.
Hi, my name is Harpreet Gill, and I get to work as the Senior Manager of Research Software Engineering team here at General's Mercy Research Institute in Kansas City. And I'm fortunate to work with multiple teams who provide software and bioinformatics services. We primarily use Azure Cosmos DB for our health device data collection platform, which collects data from a variety of health devices and transforms it into meaningful information for researchers. We collect unstructured and structured data from these devices and use Azure Cosmos DB to store them. We realized that by leveraging Azure Cosmos DB, we were able to collect a variety of datasets in one platform, then integrate with downstream processes to transform these datasets into meaningful information. It increased our productivity and made it possible for us to integrate with other platforms downstream like Synapse and Databricks.
Thank you, Harpreet, and other speakers. So one of the takeaways in this previous section was like how customers have been able to reduce their database costs with Azure Cosmos DB. And particularly interesting was the comparison between the different throughput models of Azure Cosmos DB. I found that very interesting. And by the way, we had a poll in the chat, and the question was, are you developing Gen AI applications with Azure Cosmos DB? And it seems like 57% of the audience at that time said yes. So Gen AI seems to be a very popular topic. We had 28 votes at that point. So folks, I want you to keep commenting our sessions and the topics. So please use the YouTube chat. Also go to the resources page. And again, I want to remind you all that we really appreciate your feedback. So please fill in the evaluation form. We really want to make this event better next year.
Yeah. Coming up next, we will dive into the creative uses of AI with Cosmos DB. The art is actually really cool.
Wow.
There is generative art and real-time enterprise apps with Cosmos DB, or Cosmos Conf speaking veteran, Olena Borzenko. And then stick around for the closing keynote featuring our friends from H&R Block. Let's take a look.
Hi everyone. My name is Olena Borzenko. I'm coding consultant at Xebia. And today I'm very happy to be back to Azure Cosmos DB conference. This was one of my very first few conferences when I was just starting to be a public speaker. And today I have for you a session called Turning Data into Generative Chaos. Before we will dive in, I want to give a little introduction about the session in general, why I'm doing this, why I'm talking about the art and generative art and all the other stuff. So I'm also Microsoft MVP, and my technology field is Azure Cosmos DB. So I worked with this for quite some years, and I'm really happy that I can integrate it not only at my clients and at my work, but also with my hobbies. So today's session is about me combining my hobby with my daily work, with my actual professional job. So I always loved making art, but I never get a chance to go to the art school. Instead, I ended up studying applied physics in a university. So after that, I became a self-taught software developer, and I didn't have enough time to actually do art or explore some creative and artistic things. So after working and getting myself pretty skilled in software development, I decided that I'm not ready to give up my dream and idea of becoming an artist, and I want to explore it using my professional skills. So I started building a tool to bring my hobby into my work. But before I started doing this, I had quite a journey. the last year, I had a chance to work with the CNC machine, and this is what you can see in the picture. CNC machine is typically used for wood carving, or you can have the same principle for laser cutters. But you can also put a pen in there and use it as a plotter machine. What you can see on the picture is one of my first art pieces that I did. I had to learn quite some programs that I had no knowledge in and no skills, like 3D Max and Aspire and SketchUp, to do an actual 3D visualization and then extracting the 2D image for the future printing. And it was quite some struggle for me, but I kept experimenting and trying different techniques and different colors. So this one of my other pieces, and it's kind of messy, but I did enjoy a lot the process of creating it and using different techniques. I started introducing the brush strokes and also using some acrylic paint, all this stuff. I kept working on this because it kind of was giving me a little vibe of combining art, creativity, and also math and technology. So the next pieces that I did was actually a diptych. So it's two related art pieces. And as you can see, they are related by the concept and the brush stroke. And the only thing that is different is just the 2D graphics and the color. And this was a breaking point for me because on the picture from the right side, well, from my left side, you can see this red and black brush strokes. And that's what I really liked, the intersection of brush strokes with the 2D wireframe graphics. So I started exploring it more and more, and I started working on more art pieces. And this is the results that I got. And I was really in love with them, the way how they look and the different colors and the combinations and shapes. I even made a present to my mom. So this on a white background, this was a present for my mom. She had a birthday on 27th of February, and I was standing at her place. And the last picture was one of my very experimental pieces. It actually, in real life, also have different structures. If you turn it around, you will see also nice textures. You probably can see also on my background, there's hanging another piece, which is not displayed on a presentation, but also one of my recent ones. So the thing is, I really enjoyed doing this, and I had an opportunity to do some 3D graphics visualization, improve my skills, but also use brushes and acrylic paint and do some actual creative work. However, I don't have that much time because each of the pieces takes at least 12 to 24 hours because it's layering paint and it's a lot of work to do. I didn't have time to put even more time in improving my skills, but I wanted to do more things like that. So I decided that I can use my professional skills and combine it with my creativity and do some art pieces together. So I started exploring algorithmic art, parametric art, and generative art. Before saying how I combine this, how I actually used it in my project, I want to explain a little bit difference between those things. So first of all, algorithmic art, you can use different formulas. It's not necessarily have to be one formula, but if you take those two lines and you iterate through them in a loop and you provide R parameter and angle, as a result, you will have with a consistent logic, as a result, you will have a fully deterministic output. So that's what's called algorithmic art. So the math here is procedural and not necessarily bound to a single formula, but the outcome will be always the same no matter how many times you run the script. And this is the example. The previous two formulas, I used P5GS to create this visualization, and this is the output. It's very simple, but already look quite nice. However, for complicated shapes like torus node, the one that you saw before on the previous slides, you need a bit more than just 2 lines of code and 2 formulas. So parametric art, parametric art is based on the parametric equations. And parametric equations is exactly what you use when you want to create a 2D or 3D graphics of a torus node. So this based on functions where the shape is driven by one or more parameters. And you can see on the screen, this is exactly the formula that I will be using in my project, in my implementation for rendering, creating the torus node. The thing is, what's the difference between parametric art and algorithmic art is that you're plotting points as a function of time. As you can see, X has dependency from time, from T, the same for Y, and the same for Z. So what it means, the essence of this parametric art is that shapes defined by formulas, but they are being transformed by the parameters. And the next one, so this is the examples of the parametric equations that I used for creating a very nice visuals. And it was, for me, an inspiration when I was creating my project. It was also an inspiration when I was just starting to do all those art pieces, because I do like symmetry and I do like the shapes in it. The next step here is generative art. So, of course, we know a lot about generative art, especially taking into account all those AI tools and modern technologies. We can generate picture using, for example, the DALL-E model, and this is going to be generative art. But that's not what I was interested in. I wanted to use parametric equations and algorithms and create generative art based on certain descriptions, rules, and logic. So what makes my art generative, or for example, the code that you can see on the screen, is a little randomization of parameters. So those 4 lines, they make result unpredictable. So every time when you will refresh the page, for example, or when you will re-render your code, there's going to be different shape, different result. It's going to be led by the formulas that you can see, but you will never be able to predict the outcome unless you're very good in math. So you set the rules and you let the system surprise you. And that was exactly what I wanted to achieve. I wanted a system, my project, to help me create more pieces that I will not be able to create myself, because I already have certain opinion of how to build things. And I will never choose certain parameters. I will never experiment in a way that can be experimented with code and generative art. So just a few words about the concept of the project. I wanted to take any user input data. I had a couple of iterations of this project, and in the first iteration, I thought that I can take environmental data, for example, data from IoT devices like temperature in the room or humidity in the room, and transform this data in a small, short art descriptions, and then use algorithms to generate small visualizations. I thought that could be a nice experiment, let's say. That was for my first iteration, and it didn't really go quite well because even if I wanted to generate something very simple, it was still quite hard to define which function and which algorithm to use in which case. So I decided, since I found for myself that I really like torus node shape, I decided to keep it very simple and very focused to one shape in my current application. So taking user input, in my case, I'm just providing short prompts. Like, for example, I want to see a shape that looks like a flower, or the shape that looks like a star, maybe even mentioning the color scheme. And this will be actually more than enough. This user input, this input will be taken and sent to LLM with a specific prompt. Based on this information, the LLM will generate for me our description. It will be not very long, just 1 or 2 or 3 sentences. It's gonna give it's gonna give a bit more details about the final view of the art. So, for example, the shape that looks like a flower, it will just give more details of how it should be twisted, what colors should be used, and so on. And based on that information, I will be generating a torus node configuration, which is going to have a very strict JSON schema. It's really hard to achieve with LLMs because LLMs tend to hallucinate and make mistakes and give different outputs, but so far it was working quite well for me. And the last step is visualization of a torus node using P5.js. So that was the concept. And let's have a look a bit into more technical details. As I already said, there's going to be a user input, and I'm going to have a little React page. Going to have an input field, a little button, and when I will be clicking on it, I'm going to be sending a request to my Generative Chaos API. It's going to be post request to generate our description. I also have AI project on Azure, and I have there two models. I have Dex3 large model for generating embeddings, and I have GPT-4 Omni for completion, for generating my art descriptions and creating my Taurus node configuration. So I will send a request to generate embeddings, and after this, I will create a prompt, and I will send it to GPT-4 to get the description. Generate design, generate the description of my design and actual configuration. I will save it, the embeddings and the design itself, I will save it to Azure Cosmos DB, and then I will give back to my UI Taurus configuration. I'm saving embeddings and I'm generating them because I want to be able to find similar items by user description. So for example, I can be experimenting with the flower-like shape, and I want to find similar items to this shape. So I will be using vector search, providing a sort of similarity score, and I will be getting similar art, so I can then choose the one that I like the most. And this is going to be the last step. So let's do a demo and actually have a look on how all this works. So first of all, I will walk you really quickly through actual code and show you what I implemented. So there is my Generative Chaos API. I try to keep it as simple as possible, having just one project with the controller and my services and some business logic. So I have generate design, get designs page, and search similar designs. Just 3 endpoints. The main endpoint is generate design async, and if you go there, we can see that we are doing exactly what I mentioned on what I showed on the slide. We are generating embeddings, and then we're generating design configuration. I'm using semantic kernel for this, and if you go inside, we will see that this is very straightforward. Getting required service, text embedding generation service, get embeddings, returned back. I'm not using those embeddings to generate my configuration. I'm going to be using them to save them in database for later for finding similar items. Generate design configuration is a little bit more complicated because it uses 2 different prompts. If you will have a look, so those 2 lines generate our description, and those 2 lines, they generate an actual Taurus node configuration. If you will go have a look on the prompt itself, you can see the first prompt is quite simple. So you are an assistant that transforms creative art prompts into vivid, artistic visual descriptions. So I'm providing some information, some context of how I want this description to be generated, how long should it be, so 1, 3 sentences, and I'm also providing the input. So far, it was generating quite good results, but I'm not sure if this will be enough for me, because later on, I want to use those descriptions as an art concept. And for this, I will need to take a little bit more. But for now, it was doing a pretty good job. The second prompt that you can see is quite long actually, but it also does quite a good job. So far, I didn't have a single time that I got output not as I need. So the prompt saying that you are an assistant that transform artistic visual description in a Taurus node configuration, and there is a certain rules of how this configuration should be created. So the thing is, this is the schema, and I need very strict output. I need it to be exactly in the schema. But besides this is not the most complicated part of it. The most complicated part is that all those properties, they are related to each other. So if you said, as you can see, for example, P and Q is a very base of generating Taurus node, because if they are the same numbers or they are not prime numbers, the result will be not very pleasing. It's not going to be very nice. So I'm providing all those rules and some additional rules as well As you can see, P and Q must be prime numbers, not equal, and P have to be less than Q. So I can add more and more rules to this, but I wanted to give a little bit of freedom to LLM, and even if result is not very satisfying, it's still a good experiment. So this is how the second prompt looks like. And if you go back here, we can see that I'm generating this art configuration, and I'm just returning it back. Yeah, as you can see here. I'm overriding a few properties here because I wanted to do a bit more experiments and have a little bit more control over this, but yeah, it's not, I can remove those 2 lines and results going to be just a bit more chaotic and unpredictable. So after this, I'm saving the result in Cosmos DB, and I'm returning the torus node configuration to the AI. When I want to find similar items, what I do is I'm using the same user input. So I'm sending those 2 requests simultaneously, one to generate design and the second one to find similar items. And what I'm doing, the same thing. First, I'm generating embeddings because I don't have embeddings yet at this point saved already in database or something like this. I have only user input. Having those vectors, I'm just getting all similar items, well, not all of them, but just top 5, using the vector distance function with a similarity score, which is in my configuration, but it's now set to 0.75. If you want to have almost exact items, you need to increase the similarity score almost to 0.99. But for me, I wanted to get everything that looks like or reminds me of certain user input. So I lowered it to 0.75. Yeah, so I'm getting all the results and then I'm just transforming them to my DTO because I don't need vectors on my UI, so I'm excluding them and I'm receiving back only the torus node configuration and the user input. So this is basically it. This is the main logic. The last method that we have here is just getting all the items from the container, and I did it mostly for testing purposes. So yeah, I'm not using it that often. I'm gonna do a very quick walk through the UI. So this is the React application, and I'm using React with Wide. So I have 2 pages. One is a home page and one is a gallery page. As you can see here on the UI, I have a default configuration for torus node because I don't want to open the page and see nothing. And here I have a logic. So I'm calling my 2 endpoints to create a design and to get similar items based on the user input. And then I'm rendering the torus node configuration, the torus node shape. This file has all the logic and all the calculations, all the math with all the effects. And I spent, I think, most of the time building this project, I spent building this component. I basically reverse engineered 3D Max, and it was much more complicated than what I thought from the beginning. So the configuration file is quite big, and all those properties are manually, well, not manually, all those properties, they implemented as a side effect for the torus node shape. So it's not going to be just a straight tube. It's going to have twists. It's going to have certain flat surfaces and lumps and all the other stuff. You will see the result now just in a couple of seconds, but the file is quite long. And if you ever feel interested in having a look on actual implementation, on the slides in a couple of minutes, you will see the QR code to the repository. And let's go now to the portal just for the second, because I want to show how I set up the Azure Cosmos DB. So I have my account created for NoSQL, and I have my database and container where I will be storing my designs. I also had to enable a feature, so vector storage for NoSQL API. I enabled it because otherwise it will not be working, of course. And if you go to the container itself, you also will need to set up the container policy and indexing policy to make sure that you will be able to save embeddings and do the vector search on your data. So let's have a quick look at the items itself. So I already played a little bit with the application. And that's if we will have a look inside a file. So that's, sorry. So that's how the Taurus node design looks like. We have the user input, we have a generated description that has a few sentences, and we have and we have the Taurus node configuration. So this is just serialized object because I cannot store an object as a vector data, so I had to make a string out of it. And then, of course, I have vectors that I'm using for similarity search. Let's have a look at the application itself. So this is how it looks like. This is pretty simple for now. This is just a simple grid as a gallery. What I'm showing all the results that I have in a container. I'm hiding all the other Taurus nodes because for now, I don't have a pre-saved result. So each of those cells is actually P5.js code that is rendering the Taurus node. And I killed my browser a couple of times. So I decided to hide a few of them just to make sure that presentation will not fail. But if we click on this, we will see the visualization. And you can see the forms looks quite nice and interesting. And I can definitely use some of them to create art pieces later on. Okay, so, but let's have a look on how it's actually being generated. So, for example, this is just the default configuration that you saw, and I can say flower-like shape. And I think this is enough. I will click generate. Of course, it's taking a little bit of time because we have 2 requests to LLMs and then we're generating the embedding. But we get the result and we even get some related visuals. So the related visuals, as we can see, the flower-like shape with smooth lines. And this one looks actually much better than the actual outcome. I think I need to work a bit more on the colors. But this is basically how it works. So I can do more. Star shape that looks like a star. I'm not sure what's going to generate, and if I have more of those. Okay, so I have more related visuals. For some reason, I got the same result, so I guess that can happen, or something went wrong in my code. But we also get related visual that also shape that looks like a star. So we also can see that more items were added here. So it was just generated 2 times, very similar result. That's fine. So at this point, that's all with the demo, and I will go back to my presentation. And here you go. There is a QR code to my repository if you want to have a closer look to the code itself, to the logic, and how it works. And thank you very much for your attention. Here is my Instagram, because there I'm going to be posting more of my artworks, and also LinkedIn and Twitter. Please feel free to connect. And thank you very much for your attention.
Many Jamal, Principal Architect at H&R Block.
Hi, I'm Vin Kamath, Principal Architect at H&R Block, and today we're going to talk about Azure Cosmos DB as the backbone for AI-enabled enterprise applications. We'll get started with Manny, talking about the journey we've had so far. Go ahead, Manny.
So if you really look at H&R Block, H&R Block is in tax business since 1955. In the world of distributed and cloud computing, we took a journey to modernize our tax platform about 3 years ago. The idea was to provide H&R Block clients an omnichannel service by composing the applications on a single platform. So as we try to do that, we set 2 big goals. Number 1 is being entirely cloud native. We didn't want a lift and shift or infrastructure as a service. We wanted to build from ground cloud native. And the second piece of this was to have a clearly defined bounded context following domain-driven design. And we wanted to extend that all the way to the data. So with those goals in mind, we looked at the technology landscape. And what we found that as an architectural choice, we landed on doing microservices for the clear isolations and independence. And to extend that isolations all the way to the data, we chose Azure Cosmos DB as our storage, as opposed to a traditional RDBMS. So let's look at the journey. When you look at the journey, we set out with some big positives. With Cosmos, that doesn't really have a schema, we are able to learn and adopt to the data model as we took the journey. Meaning, we didn't have to wait all the way for all the requirements to be known. We just started going as soon as the information was available to us and adopt to the changes. So this feature also allowed our developers to focus on the capabilities that they're offering and not have to wait for the others, because there was continuous adjustment. This was one of the greatest features that we had as we were developing these applications. The second piece of this, which was very important to us, is H&R Block is in a tax business which is seasonal, meaning January to April. So we don't really have that much going on in terms of load of clients rest of the time. Even during the tax season, we really have two big peaks. So what we really wanted, a system where we can not only scale out just a compute, but also the data layer. And Cosmos was basically good at it. So we use that to advantage. Then the other big piece was we had transaction systems that were responsible for read and write, and we had other systems like DataOps and other systems that's pretty much doing the read. So we were able to successfully have our read systems like DataOps looking at secondary region, while our transaction system was completely isolated and not being impacted in the primary region. So the feature of Cosmos that's globally distributed allowed us to do that. Now let's look at some of the opportunities or the lessons that we learned during our journey. The first one being, even if most tax documents is under 800 meg, we had documents that's about 20 gig. And we found limitations, not able to write the document. This is not actually a Cosmos limitation. This is a limitation that the SQL API of Cosmos that we use. So if you were to use Mongo's API or something else, this would work. The other piece of this is the way that Cosmos partitioning works is if you have a document that's more than 3K, then you're kind of the way that we work this out is compress the document, and we're good at it. So no problems there. Now, the scaling down piece that I was referring is the limitations that we ran into, and still it's a limitation, which is, when you're scaling down, you can only scale down to 10% of the maximum throughput you ever have done. So the floor in our case, when we went 10% down, that was more than what we need in the off season. So, but that's the way it works. So not bad there. Then the final piece of this that I like to call out is a clear understanding about how the consistency model works. The consistency models, there are like 5 of them. And the highest one is just strong consistency, and the one at the bottom is eventual consistency. We picked up somewhere in the middle, which is a session consistency. Now, the higher the consistency, the more the latency. For our transactional systems, we didn't want much latency, so we didn't pick the first or the top one. What we found, though, is when we were writing data, and another service is actually trying to look for the data we just written, we couldn't find it. So the way that we found and figured this out is we used a client session ID that we share and we were able to work around with that, and it worked out. So overall, the experience with Azure Cosmos DB was great. This is our third year, and we have been doing really, really good. So with that, I will let Vin go over with some of our journey in the AI space.
Awesome. Thanks, Manny. Glad you girls could join us today. I would just like to start off with starting with our journey in the AI-enabled app space. This is going to be a fast-paced session here. I have limited time, but I do want to talk about our journey as we first started to get into the generative AI space. For HRB customers, we developed and launched almost 2 years ago now, AI Tax Assist, which is a capability that lets our DIY clients ask tax-related questions, product-related questions, and get quick answers 24/7. This was an important piece that evolved our help center capability into something that is interactive, and I'll speak to how that works in a little bit. We also developed and rolled out in production self-help capability for our tax pros to help them with technical and tax prep related issues that may provide them a summary of resolutions. We also did a whole bunch of applied AI experiments, and there are several that are on the roadmap. For HRB associates, we also built and launched probably more than somewhere around the same time when we did AI Tax Assist, a private, secure ChatGPT app that uses Azure OpenAI service. We also did multiple tooling experiments with AI, such as building testing and evaluation capabilities so that the manual testers can evaluate them. All of this experience prepares us really well for what's to come in the years in the future. Let's get back to AI Tax Assist. So we went from primarily a search experience to an AI-infused conversational experience. So if you look at how we used to do in the past, and this still exists, but if you want to ask a question, how to claim adoption credit, you would get a whole bunch of questions and you have to sift through them, see where the answer is, or use our online virtual assistant, which has pre-canned questions. From there, we went to this, where you can ask a question and get a response immediately. Now, it also has chat history and a whole bunch of other capabilities, including follow-up questions, which are pretty handy. All of this was done over a record period of time, rapid application development, rapid iteration. And all of that was possible because we didn't have to worry too much about our persistence layer, which is where Azure Cosmos DB comes in. I'll just quickly go through a tech stack. Usual suspects here. We are on the .NET and Azure stack. Cosmos DB Azure storage integration was really simple considering the Azure SDKs that were available to us. And infrastructure, Azure OpenAI service, Cosmos DB, SignalR, App Gateway, all of the usual suspects, like I said. All of this enabled us to, develop and deploy this in record time. And it also allowed us an incremental uplift in client satisfaction and conversion. So this has been in production for 2 tax seasons now, including this one. If you look at this high-level conceptual architecture diagram, on the right-hand side, you see design time capabilities that we have built from multiple content sources, including our Tax Institute, which is proprietary content that we process and ingest. We have content ingestion pipelines that enable us to push it to Azure Blob Storage. We have a content indexing service that uses the embedding model from OpenAI, and we prepare an index in the Azure AI search. So in runtime, as the user queries come in, we use semantic kernel SDK, and then we run the query, embed it. We search the query, we do the retrieval part of the RAG pattern, and then we do the generation part of the RAG pattern. So the assembled custom prompt is what is finally being sent to the GPT model, GPT-4o model is what we are using. So if you look at this is a pretty simple high-level diagram, but if you unpack this, there are so many capabilities that need to be built, including the evaluation pieces. And all of that data, where is it stored? It's stored in Cosmos DB. So why did we pick Cosmos DB? One of the number one reasons why we picked it is because developer productivity. It all depends on what is your custom stack that is familiar to the developers and the team. And with your stack being on Azure and .NET, it was just a no-brainer. The schema-less rapid app development also helped us tremendously. Obviously, Manny talked about scalability, regional replication, etc. So once you have Cosmos DB, what are the kind of things that you can use it for, right? So all of these are, this is data that you can store in Cosmos DB and eventually being able to run vector search on it, semantic search on it, etc. So what happens is once you have data, the vectors can stay close to it. Today we use Azure AS Search, but for several other experiments and on the roadmap, you can think about what's possible. So this is why I spent a little bit of time developing a demo of answering that question as to what is possible when we use Cosmos DB. With that, we'll get into a quick demo. And in the demo, we're going to explore what I call functional observability. So this is not your typical infrastructure observability or your app observability. This is about data. So if you have data and you want to run analytics, there are so many ways to do it, right? So one of the questions I asked myself is, what if we could use AI to do this? So I'll quickly switch to the demo here. So with chat transcript analytics, what I did is I created a bunch of educational sample data for conversations that could happen between a tax assistant, an AI tax assistant, and customer or the user, right? So if you look at this, this is all sample data, simulated synthetic data. And this is just an explorer of that data. So a user can ask, can you tell me what the federal tax filing deadline is? And assistant comes out back with a response. And again, like I said, none of this is from our real data. This is synthetic data that we use to test possible hypotheses of how we can improve our experience. So I'll go through a few more. You can see how I've generated about 20 of them, I believe. Variety of questions. Some express frustration, some are annoyed, some are really happy. It all depends. So all of this data is stored in a chat transcript DB. So if you look here, this is a very simple data model for the chat transcripts. Role is the user, assistant says this, so on and so forth. And down here, you can see the embeddings of the conversation. So these are, you can go look at and Google it a little bit and see what are embeddings. But you can literally ask questions that are semantically similar to extract information. This is the retrieval part. In order to do that, you have to generate embeddings using one of the embedding models. So I can go through some additional chat transcripts here, but you get the idea, right? Now let's switch back to the app and I'll show you what the goal is here. So the goal is to generate something like this. I want to run analysis on this chat transcript data. So when I run the analysis, I've run some analysis already. I have sampled the data because running, if you have millions of transcripts, running all of them becomes very challenging and takes a lot of time. So I sampled the data to be able to demonstrate and showcase what's possible. So in this case, I'll zoom it a little bit. You can see I've analyzed 10 transcripts. The overall sentiment was neutral for this sample. The top topic was home office reduction. What were the common pain points? I want to know that, right? So this app uses generative AI, specifically the O3 mini model, which is better at reasoning, is used to decide, given this transcript messages and bunch of transcripts, in this case 10, how can we extract this information that we are really looking for? Why are we doing this? To improve the experience, right? To find out what we can do to make it better. So we have sentiment analysis here, we have popular topics, user expectations. What are users actually expecting out of this interaction? What are some key insights, right? So I can go back and look at some older ones and see what were the common pain points, popular topics, because this helps us. If we know what the popular topics are, we can spend more time improving that content. Now, I didn't stop here because this is a good readout. I'll quickly show you how that works. So if I click in-depth analysis, it's going to pick up 10 transcripts and start to analyze each of those individual transcripts and create analytics for that transcript. And once you have a bunch of analytics, it puts them all together and goes to the next step, which is to aggregate the results of that analysis and eventually generate final insights, save results, and present that information. That's what we saw in the dashboard panel earlier. We also have some analytics about how many, what was the average messages per conversation, what was the duration of the conversation, how long they were on, things like that. So this is really helpful for us to understand how things are working in when you have an AI assistant experience. Now, this may be enough, but what if I have more questions about this, right? What would I do? Well, for that, we have a chat assistant. So this is a little bit of meta because you have chat transcripts and you want to chat about those chat transcripts, right? So here are some examples. So I can click on one of these and ask this question. Provide me an analysis of the questions about IRA benefits, please. So one of the goals with this demo was to build a semantic kernel and generative AI capability to act like an autonomous agent who is entirely analyzing the question. What kind of data do I need to answer that question? Go ahead and do the data gathering piece, review, and so on and so forth. And if I expand this, I can see how things are happening, right? So each step is producing what is going on under the hood. And you can see these are tools that are available to the system. Sorry, it's still working on it. So the expand collapse is happening. But I'll show you what happens in the end. In the end, I get an analysis of, okay, depending on the question, IRA benefits was the question, the volume, right? What is the thematic frequency, time trends, message distribution? All of this is planned in these earlier steps, okay? And we are using the Cosmos DB vector search capability to ask those questions. I'll quickly run through the code for you to see it. But you can see all of these steps are autonomously occurring that the agent is taking place. So the agent is deciding, how do I decide how to answer this question? What kind of data do I need? What kind of tools I have at my disposal in order to answer the question? So eventually, even after it gathers the data, it formulates a response that is meaningful, right? So if you look at the insight generation step, okay, I below are the 3 key insights, and then clarification, planned use of vector search that happened. So I made it very elaborate here for technical audience so that you can see how some of the kernel plugins functions are being called here. Let me jump back to the code real quick. I'll quickly go through 2 projects here in this solution. The first one is the transcript generator. So I have a simple system prompt that was able to generate those educational examples. I have an example JSON structure that I provided. And I have a Cosmos DB service that's able to upload the transcript, set up indexing policy, vector indices, stuff that we talked about. I'm using DiskANN, which is a newer capability that was released late last year. It's best for performance and scalability if you have more than 1,000 vectors. We are using the cosine similarity here. The dimensions are 3072 using the text embedding 3 large model. Now let me quickly switch back to the app. So in the app, what's actually happening is we have 2 semantic kernel plugins, and each of them provide a bunch of capabilities. Get conversation stats, get message distribution async, conversation time metrics, get interaction patterns. We have a vector search plugin that is able to do search similar transcripts, so on and so forth. So if I switch back to the Cosmos DB interface here, during the analysis, we produced these comprehensive analysis that we earlier saw, right? So the first step was to create these analytics and embed them. And the second step was to aggregate them, which is what we did. So in the runs, that's what you saw. Things like, okay, what were the pain points, confusion over eligibility, right? So this was aggregated analytics. All of this was created by the application using these tools and functions. Now I'll go over some of the prompts of the agent. So starting with this chat agent service, as the request comes in, again, using SignalR, we are able to use the chat hub. So in the chat hub, this is where the entry point of the message is once the message comes in. So we start a step, right? We start step-by-step process and send out what we call as the reasoning transparency. In order to provide transparency to the user as to what is happening, you have to notify the client. In this case, it's the user. So this chat agent service eventually ends up using step-by-step actions, right, in order to execute what the user query is and how to find an answer for. So all of this, if you look at the evolution of from here, what you can do, you can put this into a loop. So until you have a final response, you are looping through the analysis phase, the planning phase, and the final response generation phase. All of that is happening using the Cosmos DB query plugin and the Cosmos DB vector search plugin. When all of these are put together, you can imagine if you put the data from Cosmos DB and the AI using the Azure OpenAI service, generative AI models, what actually is possible, right? You can have this run every night, for example, do its sampling, improve the accuracy of the generated analytics, and make informed decisions to improve the experience for the user. And this is not domain specific, to be honest with you. If you think about this, this can be applied to any kind of data that exists in your Cosmos DB. Any JSON document, structured or unstructured data, can be analyzed on when you put AI and data together. Thank you. Hope you had a good time with our session here, and I expect you go back and experiment with how to put data and AI together. But before you go, I do want to highlight that today is April 15th, right? It's a tax day. If you haven't yet filed your taxes, file it with H&R Block. And you can file it however you want, from home, in person, or drop off. Multiple options available. We also have a mobile banking platform called Spruce. Feel free to check it out. See you next time. Thank you.
Thank you guys for watching us. Reach out to us. This has been a great experience using Azure Cosmos DB, modernizing our platform. Thank you.
Thank you, H&R Block, and thank you, everyone. This pretty much, is about the end of Azure Cosmos Conf 2025. It's been an exciting day, and we are so appreciative of you staying with us.
Yeah, I just want to give a huge shout out to all of the speakers, contributors, and everybody who made this event possible.
And we have really learned a lot about different scenarios for Azure Cosmos DB. Obviously, everything is about AI these days. So we talked about Copilot, Gen AI, agents, MCP, and so on. Real time, which is my favorite, change feeds, and so on. A very important topic, cost optimization, lots of best practices over there. And one of the interesting topics was how to use Cosmos DB and AI together to create art. And it's really interesting and fascinating to see how AI is now in all these enterprise apps and enterprise stories that we keep hearing.
Yeah, and if you want to catch any of these presentations on your own time, all sessions will be available on demand, plus some new sessions. Brian Benz will be talking about accelerating real-time analytics with Cosmos DB and GPU-enhanced serverless Apache Spark. Anurang Dutt will cover seamless integration of Azure Cosmos DB with Azure Kubernetes service. And lastly, I will talk about getting started with Azure Document DB and open source, which is the open source engine powering Azure Cosmos DB for MongoDB.
And I'm so excited about this session specifically, Patty, because I was so excited about the open source release that we did in January, Document DB, and so I'm definitely going to watch your session again.
Thank you.
And by the way, open source is something that developers love, and we just had a poll in the chat about which programming language you're using to develop with Azure Cosmos DB, and I was actually really happy to see that Python is a clear second there. We had quite a lot of C# developers, but Python is a very interesting for us, and we actually go to different Python events these days.
Yeah.
And also, I just kind of want to remind you that there's still a chance for you to give us feedback. So please go to the evaluation form and give us feedback and help us to continue to bring to you exceptional content for next year's Azure Cosmos Conf.
Yeah, and please, I encourage you to continue learning more about Azure Cosmos DB and stay involved in our community. But with that, I wanted to thank you, Marco, for being an amazing co-host today.
Thank you, Patty. It's been a pleasure working with you and hosting you. So let's high five. Yay!
Yeah, well, goodbye, everybody.
Goodbye.
See you next year. Thank you for coming.
And have a great rest of the week. Thank you. Bye.
Thanks for being a part of Azure Cosmos DB Conf 2025.
We'll see you next year.
Thank you.
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 Thank you. See you at Azure Cosmos DB Conf 2026.